So thank you very much for the invitation. It's very nice to be here. I'm looking forward to also hearing everyone else's talks. So as Dennis mentioned, I'm going to talk about some links between sequential Bayesian inference and evolutionary dynamics. So these kinds of models have actually started appearing quite frequently in the last couple of years in the sampling world. So you might have already heard of Fisher-Rao gradient flows. So most of my talk is actually going to be not directly connected to gradient flows, but in the middle of section, I'll talk a little bit about the connection to sampling and Fisher-Rao gradient flows in particular. So this talk is based on joint work with my collaborator, Philip Wacker in New Zealand. And most of the content can be found in these two preprints, particularly the first one. So I'll present kind of the high level results in the talk. And if you're interested, please have a look at the preprints. Okay, good. So I'll spend a bit of time talking about the background because at least for me, evolutionary dynamics was a fairly new field. So Philip introduced me to these models. And once we started talking about them a bit more, we realized that there are some obvious connections to Bayesian inference that people in the community have also recognized in the past. And most of the talk will center on how we develop this connection in continuous time and continuous space. In the third section of the talk, I'll refer to this connection to sampling and Fisher-Rao gradient flows. And depending on how much time we have, I'll talk about how this new kind of replicated dynamic that was inspired by the evolutionary biology literature can be beneficial for sequential Bayesian inference in the presence of some kind of model misspecification. Okay, so from the very basic setting, what do I mean when I talk about replicated dynamics? Out of curiosity, has anyone seen these kinds of PDEs before? Okay, so a couple of people. So what we have here is in the discrete setting, a system of ODEs. So I here refers to a discrete trait. So some element from the natural numbers. It could be any indicator of some discrete quantity. So if you think of gene sequences, for instance, these are very well modeled by discrete traits. And U is a frequency vector. So how frequently do these traits occur in a population? And this quantity V here denotes what we call the fitness of the trait. So how good is this trait by some measure? So if you think of evolutionary biology, this kind of model is very natural because certain traits are better adapted to the environment than some other traits. And you might have more complicated fitness functions where the fitness doesn't just dictate how good a single trait is, but also how good a trait is in relation to the frequency of other traits in a system. So for instance, if a trait models a strategy, a foraging strategy of an individual, then if every individual in that population is using this same foraging strategy to find food, that might not be fit at the end of the day. It might be that you need more novel foraging strategies that then help you adapt better to your environment. So this kind of PDE models the large-scale dynamics or mean field behavior of a large population of individuals. So doesn't really capture all these microscopic fluctuations of individuals, or refer to it as mean field behavior. So although these models have been used in the evolutionary biology literature, they've actually been used to model systems which on the surface you might think are quite different. So an application that I find quite novel or quite neat is that it's used to model the emergence of language in a population of individuals that have no grammatical structure. So individuals might send different signals or strategies, and then in the end, there might be a certain strategy that ends up being the most fit. So there are several examples of how this very simple equation can be used to model very, very different systems. So what I'm primarily interested in this talk is, first of all, the case where we have traits that are in RD, so in Euclidean spaces, continuous Euclidean spaces. The analog of this frequency vector U is now P, so it's a probability distribution of traits in the population. I'm going to always assume that our distributions are absolutely continuous with respect to the Lebesgue, so it can just work in densities. And so this replication term has exactly the same structure as we saw in the discrete trait space setting. The only difference now that I'm considering is an additional mutation term. So mutation, I think, has a very intuitive interpretation. If you think of population dynamics, individuals mutate, genes mutate, and in the biological literature, a very common mutation mechanism is pure diffusion. So you might think of just small random exploration in your neighborhood, which in the continuous limit is well modeled by a diffusion process. So diffusion being a continuous limit of a random walk. And this V function that I showed earlier, we're going to now denote by F, meaning our fitness function of an individual trait X. And because I have this expectation here, I'm going to model this frequency dependence of the fitness with an interaction term, Z. So this particular interaction interaction fitness form was presented in the theoretical biology literature. And we're going to look at a version of this to connect to sequential Bayesian inference, and in particular to misspecified model inference. If there are any questions at all, please stop me at any time. Okay, so the problem setting that I'm interested in is best described by hidden Markov models. So I'm sure everyone's familiar with hidden Markov models. So we have a hidden state, which I denote by X, evolving according to some Markov process, where the noise processes are usually modeled by some zero mean Gaussian noise. These states are indirectly observed by an observation function calligraphic H, also with some noise. And the name of the game of sequential inference is that we have a recursive procedure to compute Bayes. So our posterior distribution at any given time, discrete time n, given all of the observations up until the current time, is proportional to a likelihood producted with a prior distribution. And the recursive nature of sequential Bayesian inference comes from the fact that we can compute these posterior distributions sequentially. So the posterior distribution at time n, when evolved through these hidden state dynamics, then forms the prior distribution at time n plus 1. So recursive repetitive procedure. So these models obviously have lots of applications. I don't need to motivate that to this audience. One in particular where it's quite impactful is in weather forecasting. So weather atmospheric systems are extremely chaotic, so it's very important to capture the distribution of initial conditions, because we know that when we evolve this under the dynamics for a very short period of time, that it can diverge significantly. So a lot of these sequential Bayesian inference methods are used in operational weather forecasting. Okay, so why am I mentioning these two seemingly disparate methods? Because, as you've guessed from my title, there is indeed a connection between these two ways of looking at the world. So as we saw from a couple of slides ago, recursive Bayes in discrete time, sometimes also referred to as sequential Monte Carlo or particle filtering, involves computing a prior distribution, reweighting this via a likelihood function to then obtain a posterior distribution. And this procedure is at a very high level analogous to what happens in these replicator mutator models. So you have a mutation of traits in a population. These mutated traits get selected out according to some environmental pressure, which we refer to as replication. So the word replication, because it refers to traits being born and traits dying out, which then yields a final distribution which is in some sense analogous to the posterior distribution from sequential Bayes. So this kind of analogy or comparison has already been made in the literature quite a bit, probably earliest in the 90s from work from Pierre. So Pierre Delmoral talks a lot about genealogical model interpretation of particle filtering. Dennis has also done some work on a probabilistic interpretation of replicator mutator dynamics. So this connection, particularly in discrete time and discrete space, is already somewhat well established in the literature. So what we wanted to do was to look at how this connection extends to continuous time. So the continuous time filtering problem in its most mathematically rigorous form involves replacing those additive Markov models with SDEs. So the hidden dynamics now evolves according to this Ito SDE, where the noise term now consists of a Brownian increment. And the measurement process is also given by an Ito SDE, where the hidden state is measured in some sense by this observation operator H, but is also noisy. This is not the only construction of the continuous time stochastic filtering problem. It's just probably the most basic one. So we know that if G and H are linear functions of X, that the solution to this continuous time filtering problem is given by the Kalman-Bucy filter. So you've probably all heard of Kalman filtering. So the problem now in continuous time sequential Bayesian inference or in filtering is to estimate this continuous time sequence of posterior distributions. And it turns out that for this particular problem that I have in equations 3 and 3a and 3b, that the evolution of the unnormalized densities is given by this equation at the bottom, which is known as a Zakai equation. And the nice property of these filtering equations is that we have a separation of evolution under the hidden state or the hidden dynamics or the signal, plus a correction term that accounts for the observations or the likelihood function. So one notational aspect, I'm going to use this operator calligraphic L star in a somewhat general way. If it gets confusing, I'll please ask, but I'll try and explain what it means in each context. So here, this object means the evolution of the density under the signal process. So it corresponds to the adjoint generator of the hidden state. So you might already be thinking, okay, this has a nice analogy to the replicator and mutator equation that we saw earlier on, which also had this mutation plus replication structure. So that's kind of what we're getting at here. Okay, so why should we bother caring about continuous time? Well, from an analysis point of view, it's usually much nicer to work in continuous time than in discrete time. On top of that, if we're working with very high frequency data that is best modeled by stochastic differential equations, which often comes up, for instance, in math finance, it's useful to look at the filtering problem in continuous time. On top of that, it's also helpful, I think, to be able to construct diffusion methods to approximately solve the continuous time filtering problem. So by that, I mean that we can have a whole entire class of methods wherein we have what I call a mean field process in equation 5. So this is a process that governs the evolution of individual particles. It's a McKean-Vlasov diffusion or an interacting diffusion because the evolution of each particle depends on the position of other particles. And this dependence in the mean field equation arises because these coefficients U1 and U2 depend on rho t bar. So rho t bar here is the distribution of this process X at time t. So there's been a whole zoo of methods of this type. There's a few references below, but the name of this game is basically to start off from this very general diffusion process and then to say, how can we determine the form of these coefficients U1 and U2 such that the law of this process coincides with the posterior distribution that we saw evolves according to this Sakai equation. So the normalized version of this Sakai equation is what's known as the Kushner-Stratonovich equation. So not so important. Okay, so that's the background. Okay, so the main reason we were interested in formulating this connection more precisely was because it's often useful to then facilitate some crossover between the two fields, which is then what we sort of started to do, which I'll talk about at the very end, with this fitness function that comes from evolutionary biology, and I'll show how it helps with this misspecified model filtering problem. Okay, so the specific type of replicator mutator equation that I'm interested in to relate to the filtering problem is this one on the board here. So equation 6 you've already seen. It's a mutation plus this replication term. As you might have already guessed, the mutation term is quite easy to link to filtering because we can just make that equivalent to the hidden process. The replication part becomes a bit more tricky because we're dealing with continuous time data. So most of the work comes in resolving how to think of this continuous time process. So the fitness function that we're going to look at is equation 7. So if you just ignore this second term, the first one looks very much like a least squares term or a fit to a data. So y subscript tn is going to be data points at discrete time points, and h here is going to be this observation function that relates the hidden state x or traits to our observations. So the reason we consider this kind of fitness function from an inference point of view is because we typically have access to discrete time observations that come from this kind of model that I showed very early on for this discrete time problem. So this Tn refers to a discretization of a time interval. I'm going to use delta to refer to the spacing between time points. And a measurement y, Tn, which relates to the hidden state at the same time Tn plus some noise. This second term here will give us something that isn't going to coincide with sequential Bayesian inference, but has interpretations from a generalized Bayesian inference point of view. I won't talk about it in so much detail, but please feel free to come and ask me afterwards. From an evolutionary biology point of view, it reflects something that prioritizes conformity or diversity in a population. So depending on the value of S, particularly whether it's less than 0 or positive but less than R, it will prioritize individuals being similar in traits. From an inference point of view, X being more closely clustered together, or diversity meaning greater spread. Okay, so since we're interested in a continuous time problem and how we can bridge this discrete time version to a continuous time version, the natural question we might ask is then, what happens to this PDE, which has on the right-hand side a term that is only piecewise continuous? What happens to this PDE as we let this time interval delta go to 0? So that's our first question here. And going to jump straight to the theorem. As you might have guessed, for the special case where R is equal to 1 and S is equal to 0, so we don't have this conformity versus diversity term, we get that as delta goes to 0, this PDE converges in a suitable sense to the Zakai equation. So the main theorem is in our paper, so you can look at theorem 3.1 in the preprint. We actually show this result for the more general case of involving this term with diversity and conformity. But I think just to introduce the main point, it's nice to see that as delta goes to 0, it's this particular type of fitness function that gives us a connection to the continuous time filtering problem. I go till 10:50, right?
Yeah.
Okay. Okay, so I'll talk a little bit about the proof because I think it's quite an interesting point, especially if you come from the stochastics world. So we saw that the continuous time filtering problem consists of these two SDEs, but a problem that is more closely related to the replicator mutator equation with this piecewise continuous fitness function is this form here, where we have continuous dynamics in the signal process, but a discrete time measurement model. And the way in which we can relate these two equations is to then determine how we can understand, I wanted to write things down. Yeah, amazing, okay. So the way we wanted to, so the important point is to be able to understand this measurement process in a way that in a limiting form can be seen as the kind of SDE that we saw in the continuous time filtering problem, this one here. So the main insight is to see that the way we need to interpret this measurement process is that it comes from a piecewise smooth approximation of this SDE. So there are many different ways you can see this approximation. I'm just going to draw the most simple form. If you have time in the measurement process. So if you think of a realization of this iter SDE, it's going to look like something very rough, continuous, but rough, not differentiable in time. An example of this piecewise smooth approximation would be that we have discrete time points that correspond, for instance, to exactly this time interval where the discrete measurement process comes from. And we construct, as the name suggests, a piecewise smooth approximation to this rough signal. So obviously, the finer your time increment, the better the approximation to this very rough signal. And the gradient, so it's piecewise smooth, it's differentiable within the time intervals, obviously not at the endpoints. And the gradient of this process is then going to coincide with this particular measurement process with a suitably defined covariance. So you can do different kinds of polynomial approximations within the intervals. Linear is just the simplest one. And a lot of this is looked at in quite some detail in rough paths, for example. So this is very much baby version. So I'm going to use this delta here to denote this, that I'm referring to this piecewise linear, piecewise smooth path. So the reason this is important is because these particular kinds of approximations, when you let the time interval go to 0, converge to what's known as Stratonovich rather than iter SDEs. Is everyone familiar with seeing some nodding? Okay, good. So brief recap. When you think of stochastic calculus, the way in which you approximate stochastic integrals can lead to different kinds of interpretations. So if you think of Riemann integrals from regular calculus, if you split up the function that you're trying to integrate and you evaluate these functions either at the left point or the midpoint and look at the limiting object, it doesn't make a difference whether you evaluate at the left or the midpoint. You end up with the same Riemann integral at the end. So this is quite different in stochastic integration. Evaluating at the left point gives you what's known as an Ito integral. Evaluating at the midpoint gives you what's known as a Stratonovich integral. Stratonovich integrals are nice in that they preserve a lot of the ordinary calculus rules. Ito integrals don't, but they have nice, what's known as martingale properties. Okay, so the reason we pick this particular type of approximation is because this form is key to obtaining the Sakai equation as the limit. So if you took a different kind of approximation, you wouldn't actually get this connection to the Sakai equation. Okay, so to see that this is indeed true, we first need to construct the corresponding filtering problem with this piecewise smooth approximation to the data. A form of this has actually been looked at in the stochastic filtering literature. And then the name of the game is really in looking at what this limiting object looks like. So if you've heard of Wang-Sakai theorems, this has laid a lot of the groundwork for these kinds of results. We're now working with limiting objects of PDEs rather than ODEs, but a lot of the techniques are more or less the same. I think the only key insight that's really worth pointing out is that if you accept that this piecewise smooth approximation converges to a Stratonovich rather than Ito integral, so this little circle here means Stratonovich integral, there's a way to convert between Stratonovich and Ito integrals. It's known as the Ito-Stratonovich correction. So the only thing to recognize is that if you then convert this object to an Ito integral with an Ito-Stratonovich correction term, then you get rid of this middle one here and you get back the Sakai equation. So this is the only real kind of observation that you need. The rest of it is really just in technical details. But the key point is that this approximation that converges to a Stratonovich object is really important. Okay, and then just a bit of numerics to hit home that this interpretation is important. So this plot just shows intermediate densities from a linear Gaussian filtering problem. So we know if the problem is linear Gaussian, we're going to have Gaussian intermediate densities. It's just Kalman filtering. The red is the initial density. The blue is the solution of this replicator mutator equation with some discrete observations, discrete in time observations. The black, which is sitting pretty much underneath this blue line, is the solution to this filtering problem with the Stratonovich interpretation. So you can see that they do indeed align, which is why this is the correct one. And the pink is if we'd incorrectly assumed that the correct interpretation is an Ito one. So they're quite separated. So even in this linear Gaussian setting, it's important to make the correct interpretation of this discrete problem. Okay. I'll now talk about the inverse problem, sampling problem, which is a little bit more connected to gradient flows. So from my point of view, it's at least possible to see a certain kind of Bayesian inverse problem as a special case of a filtering problem where there's no signal dynamics and there's just a measurement process that's looking to recover a single state or an initial condition. And using exactly this theorem that I showed before, it's then very easy to reinterpret this replicator dynamic now. So no mutation because we have no signal dynamics, but just a pure replicator dynamic. And with this fitness function, where you have no conformity or diversity term, just the least squares type fit, you end up with a direct connection to continuous time Bayesian inverse problems. So at time equals to 1, you get back your posterior distribution. If you let time go to infinity, so you keep running this replicated dynamic, then you end up with maximum likelihood estimation. So you completely forget your prior distribution. So the initial distribution of the replicated dynamic. And these kinds of dynamics are interesting from a sampling point of view because, finally getting to gradient flows, they have a nice interpretation as a gradient flow with respect to a specific metric. I probably don't need to talk about gradient flows too much, but what I'm talking about here is gradient flow in the space of probability densities. This object here is the Frechet derivative of some functional, usually an energy functional. And this calligraphic K is some kind of dissipation mechanism that tells you how quickly energy is dissipated. So one very typical example that comes up in gradient flows is when this dissipation mechanism is taken to be an inverse metric tensor. So there's been a couple of results of this nature in the literature now. It's now somewhat well known that the relevant metric for this replicated dynamic is indeed the Fisher-Rao metric. So the Fisher-Rao metric, unlike the Wasserstein metric, has nice invariance to reparametrization properties. The result that's relevant for the particular kind of replicated dynamic that we look at is that it's a Fisher-Rao gradient flow of the average fitness functional. So remember we said F here is this fitness. It can have this non-local structure. So this replicated dynamic that we showed, that I showed in a couple of slides before, is a gradient flow of an average fitness over the entire population. So integrating both of these components of the fitness. So yeah, there's a few papers that have looked at this in specific contexts in sampling, most notably Fisher-Rao gradient flows of the KL divergence. Apologies if I've missed out some other literature. From an evolutionary biology point of view, this was mostly known as a gradient flow with respect to the Fisher information or Fisher information metric. They also call it the Sahani metric. So we mainly looked at extending this to continuous spaces and to non-local fitness functions. And with this theorem, you can obviously then easily connect to sampling methods that have now been proposed in the literature. So this first one here is the Fisher-Rao gradient flow of the KL. I've written its unit time version because it's easier to connect to local fitness functions. But you can also then very easily obtain a connection to Fisher-Rao gradient flows of the maximum mean discrepancy that do have this non-local structure that we don't very easily connect to Bayes. So remember we said that Bayes doesn't have this non-local term. Okay, how are we going? So I'll spend the last bit of the talk on this misspecified model filtering problem and this non-local fitness term. So the reason we wanted to do this was because this squared fitness term was very easy to connect to Bayes' theorem, but it wasn't so easy to see what it was doing from an inference, what the other term was doing from an inference point of view, this conformity diversity term. And as we started to look into it a little bit more, we realized that there's some connections to techniques that people use in the data assimilation community, which is known as covariance inflation. And this is known to be very useful for this misspecified model filtering problem. So we looked at a specific form that helps to improve on dealing with this misspecification in a way that's not usually done. Okay, so for demonstration purposes, we really wanted to just look at the linear Gaussian problem to get a sense of what's happening. So the top equation is just the replicator mutator equation that you've seen before. This term here is just the generator of an OU process, Ornstein-Uhlenbeck process. So we're in the linear Gaussian setting. And then the bottom line is this fitness function, again, in the linear Gaussian setting. So I've just rewritten it and made use of this smooth approximation to the observations. So thanks to the theorem that I presented at the very beginning, we know what this object looks like in the continuous limit, and it has this structure here. So key point is that if you ignore this bottom line, or in other words, if you set S to 0, then you get back the usual equation from filtering, the Kushner-Stratonovich equation. So this non-local term adds an extra covariance type term to the filtering equation. So with this, what we can get is that we can now very easily write down corresponding mean field processes that describe how this density evolves. So you may remember at the very beginning of the talk, I showed these diffusion processes that we can construct whose distributions evolve according to the filtering equation. We can do something very similar with this modified Kushner-Stratonovich equation. And in the linear Gaussian setting, we get back something that looks a lot like the ensemble Kalman-Bucy filter. So the ensemble Kalman-Bucy filter, for those of you who aren't aware, it's basically a particle-based version of Kalman filtering, very useful when you have nonlinear drift functions. So this first part here is just the usual evolution under the signal process. This second part here is what's known as the Kalman type innovation. There are different ways of writing this. I've just written one type. And this term here is this extra term because of this non-local fitness part. And it acts as a kind of covariance modification, as I mentioned before. I think Dennis has also recently put out some work called the nudging Kalman filter, which looks very similar in structure to this kind of problem, to this kind of model as well. Okay, so I sort of talked through everything that was on this slide. But if you take a specific setting of these parameters, you get back a well-known model in the ensemble Kalman filtering world called covariance inflated ensemble Kalman filtering. It's a very nice review of all of these different formulations from Pierre Dalmoral and Adrian Bishop in their 2023 paper. This is just one of these types. So this covariance inflation is a technique used by the practitioners to deal with a whole array of issues that come up with doing sequential inference in practice. So some of this being due to model misspecification, but also due to sampling errors. So they tend to use very small sample sizes to solve the filtering problem because it's just not practical to use very large sample sizes in the kinds of problems that they deal with. Okay. All right, so I have like 3 minutes. So I'm just going to very quickly summarize the findings in the context of misspecified model filtering. So long story short is basically that this kind of equation where you have this covariance modification term, first point is that it coincides with a combination of two kinds of covariance inflation methods that are used in the practical data assimilation world. And second point is that using a combination of these methods rather than using one of them by itself gives you a better mean squared error approximation. So a more robust approximation of the hidden state when you have some model misspecification, better in the sense of mean squared error, minimizing mean squared error. And on top of that, this combination of covariance inflation methods gives you a posterior covariance that's more representative of the uncertainty in your system. So the problem is specifically that using one of these methods can give you an underestimation of your covariance. It can make you artificially overconfident about the hidden state. But using this formulation with a good choice of these S and R parameters gives you a much better representation of your uncertainty. So that's the kind of bigger picture summary of this last section. And we looked at a very specific problem to demonstrate this point, where we have the classical linear Gaussian filtering problem, but some constant bias term that we don't know. So the observations are generated from this model, but we incorrectly assume that this bias term is 0. So the quantities that we're then interested in are the error and the squared error. And when this bias term is non-existent, we know that the covariance from the Kalman filter exactly coincides with this squared error. But when we have a non-zero bias, this will no longer be the case. So we need our covariance to actually represent the total mean squared error. And that's the benefit of having this conformity diversity term. It gives you a covariance that actually reflects the mean squared error. So again, if you want to see some more details, this is mainly summarized in these 2 lemmas in our paper. Also, you can come and talk to me about it. The second point is maybe the more interesting one, which is that if you choose this kind of inflation that's most commonly used in the data assimilation literature, which corresponds to this S term being equal to 0, then you have a covariance that's severely underestimating the actual mean squared error in your problem. The second point is also that you have an infinite number of R and S values that you can choose to minimize mean squared error. This is unsurprising. You're trying to minimize one quantity with 2 parameters. And the point is really that choosing an R and S value that not only minimizes mean squared error, but also gives you a covariance, a posterior covariance that's equal to the mean squared error, coincides with one specific choice of R and S parameters. So that's what we characterize in this lemma that I showed before. And this plot is just to demonstrate what the contours of different R and S values look like. So the colors correspond to different mean squared error values. The red line is all the possible R and S values that give you the smallest mean squared error. And the left is just what we get from the theoretical calculation, and the right is just from a particle-based application, so they coincide quite well. And the last plot is just to hit home this point that I was making, that if you do this additive covariance inflation, multiplicative covariance inflation that's done quite often in the literature, which corresponds to S equal to 0, then you end up with an optimal R value, which in this case is quite large, and it gives you an asymptotic covariance, the C, which is quite small. So the y-axis here gives you a covariance of less than 0.1. The pink line is the asymptotic covariance if you had perfect knowledge of your system, so a lot larger. So the point is really that you shouldn't just inflate in this multiplicative inflation method because it's going to give you a covariance that's much smaller than what you would get even if you had perfect knowledge of the system. So the blue line is the optimal choice of R and S that gives you a covariance that's actually equal to the minimum mean squared error. And that was basically it. So I talked about lots of different things. Main points are there's obviously a connection between replicator mutator equations and sequential Bayesian inference, particularly in continuous time. as a nice connection to Fisher-Rao gradient flows from sampling. And this non-local fitness function that we inspired by the evolutionary biology literature gives us a nice way of dealing with model misspecification from an inference point of view. That's it. Thanks, everyone.
I'm going to talk about several recent works on tempering, so for Langevin dynamics. So the application is mainly Bayesian inference. And yeah, so let's go. Let me introduce first the problem. So we were interested in Langevin dynamics, so where the goal is to sample from an unnormalized density mu star that is proportional to some exponential minus v, where v is a known potential. Okay, I have access to v. So a standard process to sample from this mu star is a Langevin diffusion that is basically written as equation 1, where you initialize your process at some proposal distribution mu that you can sample from, like a Gaussian, for instance, and then you run this process. Okay, so this Langevin diffusion has, under very mild conditions, as a stationary distribution mu star, which is the object of interest. And in practice, you can very easily simulate it or approximate it in discrete time. So it's an algorithm known as EULA, unadjusted Langevin Monte Carlo, or LMC, Langevin Monte Carlo, that uses a step size h, and you just discretize the previous diffusion as the following iterates here, where z is a Gaussian, standard Gaussian noise. Okay, so this is a Langevin algorithm. And so it's a workshop on gradient flows indeed. So there is it's hidden behind our work, but I won't talk too much about it neither. So one of the convenient things as well with the Langevin is that you can see its marginals, ρt, at each time, as following a gradient flow of some objects that is a Kullback-Leibler divergence. What does it mean? It means that the marginals ρt of xt satisfies this equation. This is a partial differential equation ruling the evolution of ρt. And this object here is actually the gradient of this object that is a Kullback-Leibler divergence. So it's a divergence between probability measures, quantifying how far ρt is from mu star. And it's a gradient with respect to the Wasserstein-2 metric. Okay, so this is very useful. It's known since this paper in '98, and it has been used a lot in the analysis of discrete Langevin approximations to get rates for Langevin algorithm, like for instance, since this paper in 2018. And in particular, when you're in a very friendly setting, when mu star, your density of interest written as exponential minus v, is strongly log concave. What does it mean? It means that v is alpha strongly convex. So you can think, for instance, as a quadratic, like a Gaussian. Then your Langevin diffusion will converge very fast because the objective, the KL, will be an alpha convex objective in the Wasserstein-2 geometry. And you can obtain fast trace both in the distance to the iterate, which is the Wasserstein-2 here, the underlying geometry, and the objective that is the KL. Okay, so these rates are actually exponential in alpha, where alpha is a strong convexity constant of V. Okay, so if you think of a Gaussian that is very peaky, you will converge very fast. Okay, and I just recall very quickly the Wasserstein-2 distance, but I think everyone here is familiar with. And I didn't say it, but of course, feel free to interrupt me anytime with questions or to clarify notations. Okay, so I've said just before that Langevin is known to converge very fast when your potential is strongly convex, like a Gaussian, for instance. However, you can relax these conditions to some other forms of relaxed strong convexity. So these forms of relaxed convexity are called functional inequalities in our setting, and they are called Polyak-Uryazevich conditions in optimization. These conditions write as follow. It means that the gradient of the objective you optimize, the square norm of the gradient, dominates the function. Okay, so these conditions are known to imply that there's only one global optimum, and that the critical point is, where your gradient cancels, basically you're at the global optimum. And these are the minimal assumptions so that your gradient flow converges very fast. The reason is that if you look at how fast your objective decreases along the dynamics, like here, I look at how fast my function decreases along my gradient flow, you can show easily that this is proportional to the square norm of the gradient. So now, if you know that the square norm of the gradient dominates your functional, you will get very simply with what is called Grunwald lemma, a very fast rate proportional to the constant beta that was in your functional inequality. So in the specific case where we are interested in a functional f that is a Kullback-Leibler divergence, as in Langevin, there are functional inequalities that are known to characterize this for the Kullback-Leibler divergence. So more precisely, these two conditions of interest are the log-Sobolev inequality, which is this one. So it's an inequality characterizing mu star, so that I wrote here. But basically, you can show that this rewrites as the Kullback-Leibler divergence to mu star satisfying such a functional inequality. Okay, and if this Poincare inequality is the second inequality, you can show that this characterizes that the chi-square divergence, which is another divergence, but along which you can measure the decrease along Langevin dynamics, this will satisfy as well a functional inequality. Oops, sorry. So my message here is that we knew already that Langevin was working very well when I had a strongly convex potential, like a Gaussian, but I can actually consider these weaker conditions that are the log-Sobolev inequality and the Poincare. Actually, each of these, as written at the bottom of the slide, is a relaxed version. Okay, so if I know that I'm alpha strongly concave, I satisfy LSE and the Poincare. And actually, if you're alpha strongly concave, the constant of interest is 1 over alpha. So basically, you want alpha to be very big or the CLSI constant to be very small. This will characterize how fast your dynamics of Langevin converge. However, these constants that characterize how fast Langevin dynamics converge are not always good in practice. A simple example is a mixture of Gaussian. Here I took a mixture of two Gaussians. So mu star is in 2D. I have located at m and minus m. Okay, so not exactly like on the draw, but think of this guy. You can show that actually the LSI constant will be very big and lower bounded by something exponential in the distance between the modes. Okay, so this is very bad because basically my rate will be governed by minus inverse of this constant, so which is very small, so it will be very slow. Okay, so these conditions satisfying a log-Sobolev inequality is very general, like Gaussian mixtures satisfy the inequalities, but with a very poor constant. So in practice, you will see that your algorithm does not converge. Here it's a simple example where you launch Langevin. The targets are the blue are represented by the blue samples, and Langevin will spend in practice an infinite time in one of the modes. Okay, so this is something very known from practitioners, and it's a problem. So what people have been doing is to consider tempering strategies. And the first work I will present is about strategies related to what is called geometric tempering. So I will explain. And it's a joint work with my postdocs Omar Shehab and Adrien Vacher and my colleague Austin, who are all in my lab at CREST ENSAE IP Paris. Okay, and this paper will appear at iClear very soon. So the idea of tempering is to do the following. Instead of targeting mu star directly with a Langevin-based algorithm, maybe I can consider a sequence of capital K intermediate distribution. Okay, so mu0, starting from some nice proposal mu0 that I know how to sample from, up to mu star, that I hope are better condition. Okay, so less multimodal with a separated mode. And I will run Langevin to target each of these intermediate distribution. Okay, so in practice, if mu I is written as well as a density proportional to exponential minus vi, basically I can write this strategy as follows. So my Langevin diffusion for some interval of time will target sequentially this sequence. So first question, how can we choose this sequence mu I? So there's a very let's say a popular strategy that is to choose what we call here a geometric mean. So a geometric mean writes as follows. So I can consider I fix a proposal mu, like a Gaussian, for instance, once again. I have a fixed target mu star that is maybe very complicated, like a mixture of Gaussians. And I consider these intermediate densities, mu Si, that are basically proportional to mu to the power 1 minus lambda Si times mu star to the power lambda Si. Again, I consider this lambda to be between 0 and 1 and increasing. Okay, so if lambda is 0, I'm at the proposal. If lambda is 1, at a mu star, and in between, I interpolate. So here, for instance, I represented, so mu star is a mixture of Gaussian, and mu is a standard Gaussian, centered at 0. And I represented the interpolates with the different values of lambda Si, but that are increasing. Okay, so you see that quite nicely, it is still unimodal. It has one mode for several Si, and then it starts to split. Okay, so you may think maybe it's helpful for Langevin so that my particles go in this mode, and then they spread as the Langevin diffusion is targeting the next sequences. Okay, yeah. This one. Okay, sorry. Okay, so this is a strategy that is very popular. The main reason is that recall that Langevin diffusions were using some gradient of the potential, right? I had some grad V if mu star was exponential minus V. And here, if I consider these sequences, I can also have access to the scores, right? The gradient of log mu Si is simply a mixture between the score, so this quantity is called the score of mu, and the score of mu star. Okay, so this guy I have access to because I know V, so I know grad V. And this one, I can choose a Gaussian, for instance, so I know as well this one. Okay, so on a practical point of view, this is very easy. I just need to replace grad log mu star with this quantity. Interestingly, so I don't talk about this work here, but it's a work I've done with my colleague Nicolas Chopin and Francesca Crotigno, who's a co-organizer today. This sequence is known to be a discrete time version of a Fisher-Howe flow, so of the Kullback-Leibler divergence, so the same object that is decreased in the Langevin dynamics, but this time with respect to not the Wasserstein two-metric, but the Fisher-Howe one. Okay, so we were interested in these questions. What rate of convergence can we obtain under standard functional inequalities? So like the relaxed, strong convexity assumptions I've showed you before for these strategies of geometric tempering. Second question, does there exist an optimal tempering scheme? Like how can I choose a sequence of lambda? Should I do a grid between 0 and 1? Should I go fast or slow? And does it improve over vanilla Langevin, which is the main thing of interest? Is it worth, is it a good strategy? The answer is a bit no, but I will spoil, sorry. Okay, first check, let's check the upper bound. So the framework is the following. I know that my tempered Langevin dynamics writes as follow. Okay, so I have written it in continuous time, but basically I have a sequence of target mu s, okay, that is a geometric mean between mu and mu star. That is basically the stationary distribution of a Langevin, of a Fokker-Planck equation that is ruling the Langevin diffusion evolution. So this is basically what we want to characterize the convergence of rho s to pi, to mu star, that is the final target. And in practice, the counterpart, the object in RD that is associated to these partial differential equations are these Langevin diffusions where we have a potential Vs corresponding to this mu s interpolating between the proposal 1 and the target 1. And I'm following these Langevin diffusions where the potential is also moving with time. Okay, so this is the main difference with standard Langevin diffusion where you would have V that is fixed. So for the analysis, it's important. Okay. So we need few assumptions to characterize how fast these Langevin diffusions converge to the target. We need some mild assumption on the sequence of temperatures. We need them to be piecewise continuous, and we need them to be increasing, okay, which is y lambda dot, the time derivative is positive. Second, we need this kind of assumptions. So what do they say? So these assumptions are called the dissipativity assumptions on the potentials of the proposal and of the target. And they lower bound this scalar product between the gradient of the potential and x. And basically, these conditions, you can think of it as being relaxations as well of strong convexity, and they are related to being strongly convex outside the ball. So what does it mean? Here is a small figure image. So if you think of a mixture of two Gaussians, the associated potential would look like this, the V, and this guy is not convex, right? But if I cut here, it would be convex outside of a ball that is minus 4, 4. So the reason why we make these assumptions are the following. Under these assumptions, we will be able to derive rates, and in particular, the second one enables us to say that along the sequence of tempering, all the distributions have a finite log Sobolev constant, which is exactly what we need to characterize the speed of convergence. Once again, feel free to ask questions. Okay, so this is the bound we obtain. What does it mean? So at all times, I want to characterize the convergence of the KL to my target mu star. I have ρT, that is the law of my Langevin diffusions following this annealed or this intermediate sequence of distributions interpolating between proposal and mu star. And they are smaller than the constant. A, so A is a constant depending on the constants of my problems, and this quantity GT. And GT is a function depending on time, on the sequence of temperatures lambda, okay, that are between 0 and 1, and on alpha S. And alpha S, I say it here, basically they are the inverse log Sobolev constants of my sequence. Okay, so what does it mean? I said I have an initial distribution mu, a target mu star. I am looking at the interpolation, and I hope that these guys have nice log Sobolev constants, which mean that they are not too multimodal. Okay, so these quantities, they appear in my bound. So we were able to derive this. The nice thing is that first, if we don't basically consider annealing and we directly aim at mu star, we recover known rates on Langevin, but we generalize them. The second thing is that now that we have done this, we are able to basically, if we know alpha S, the log Sobolev constant along the path, maybe we can derive this sequence with respect to lambda and see what happens. Okay. So this is what we did, but the issue is that, oh, sorry, it's cut here, but it's not on my screen. Sorry about that. The issue, so I didn't say it, So it's generally hard to characterize exactly what are the log Sobolev constants between in interpolation. One case that is easy is when both mu and mu star are strongly log concave. Okay, so this is not the most interesting case in practice because you can think of two Gaussians, and in this case, we are able to characterize what are the log Sobolev constants along the path. In the general case, it's very hard. Okay, so there are papers from people much more technical in the PD community doing this kind of stuff, but yeah, it's very hard. If I have two Gaussians, if my two distributions are strongly log concave, I actually have this very simple inequality saying that the inverse log Sobolev constant or the strong convexity constant are basically a mixture between the initial one and the final one. So when we have this relation, we can plug it in the bound I had before, and we can optimize it with respect to lambda. Okay, lambda, recall, is the schedule of temperatures I consider. And we find the following. We find that if alpha mu star is too big, which means that my target is very picky, like think once again as a Gaussian with a small variance. very strongly convex, then there's no interest in tempering. There's no point. You should basically directly target new star. If, in contrast, is flat compared to my proposal, then I have an interest in tempering, like not directly targeting mu star, but considering a sequence of temperatures that are interpolating between 0 and 1, and in the following manner. So in this plot, I've shown numerically what it gives. Like this orange curve would be the convergence of vanilla Langevin. If you directly, you don't do annealing, you just directly target mu star. Okay. The blue one is the bound given by optimizing over the schedule. Okay, so we are very happy. It's below. This is what we wanted, and it tells you that you have an interest, like in short times, you will be much faster than Langevin. Okay, so you will gain a lot of time here. Eventually, they will the curves will merge. And another interesting thing with our bound is that here we optimize over the lambda, but in principle, you could plug any schedule of temperatures that you would like to try and look at what the bounds tell you. And this is what we did with the green curve here. The linear tempering is simply a linear grid, like proportional to the time. So sorry, it's not written here, but basically it's S over T, where S is between 0 and T. And you can see that in short times, it's better than vanilla Langevin. So you have this interest of tempering, but then in longer times, you will converge less fast. Any questions on this? Of the green? So yeah, so it's not written here, but basically when we take our bound, I take the strongly log concave case where I know what this alpha S in between look like. They look like this. Oops. So I can plug it here. And then I plug lambda S that is S over T. Okay. So it's linear in S. And then I integrate. And basically we get a bound that is of order 1 over T instead of exponential minus something in T. So we see that, yeah, it will be better in short times, but not in the longer time. Thanks for the question. But yeah, this is what was nice with our bound, is that you can basically play with them and see what your schedule would look like. Okay. All right. So yes. So there are several issues with what I presented. So first, we can only really interpret our bounds in this strongly log concave case, which is a bit limiting. And then these bounds, these upper bounds, tell you how fast Langevin converge in the worst case, right? You have a bound that looks like your KL between rho T and nu star is smaller than something. Okay, but this maybe your KL is much smaller. Okay, so these are worst case bounds. So we were interested in lower bounds. Can we characterize if these bounds are tight in some sense? Okay. So first result I'd like to show is actually we could say some additional things beyond the case of log concavity. So what do I mean here? We could show that the geometric tempering strategy had issues even when you have a very well conditioned proposal and target that are unimodal. So this is the case in my drawing. So mu, my proposal, is this blue Gaussian, and nu star is almost a Gaussian, right? It's this yellow density. It's the mixture of a Gaussian and a very small perturbation that is a uniform, but it's still unimodal. It does not have two modes. We needed to do this for technical reasons, okay? That I will explain in one sec. And then we look at the sequence of geometric tempering, and you see that even if my proposal and target are unimodal, in between I will have two modes, okay? Which means that Langevin typically will get stuck in one of these modes. So this is a problem. It was even better to do Langevin from the start. So this is a case where we see that doing geometric tempering can be worse than no tempering at all. And this proposition says it in terms of functional inequalities. It says that you can have a well-conditioned proposal and targets. That means that they have small Poincaré constant that are 1. And here Okay, so this does not seem small, but it's polynomial in M. That is the size of the mode or the perturbation. But you can have an exponential worsening of the Poincaré constant in your sequence. Okay, so this is what this result tells. But this is really, you should have in mind the picture. In between, you create some multimodality, which is exactly what you want to avoid. Okay, so this tells us what happens in terms of constants, in terms of functional inequalities. It's not exactly a rate. So this is what we do in just after. We have two results. So one is in the case where we have a multimodal target, which is a mixture of Gaussian. And the second one is the example I just showed before. And basically, these results tell us that, yeah, so I tried to summarize it by the question above. I could think that maybe I have very bad interpolates in between, but maybe the geometric, what to say, sorry. Maybe my Langevin diffusions targeting the following distributions would avoid these distributions, but the result is no, and this is what we show with these bounds. We show that, yeah, under mild condition on the temperatures, we can lower bound the total variation between the target and the sequence of Langevin diffusion by something that will remain positive. And this is the amount of time that is spent, and this is the distance between the modes. Okay, so happy to spend more time on it if you have questions, but basically, this is what these results say. Okay, so to conclude on this part, what we've done and what we've concluded is that geometric tempering is a very popular strategy because it's very simple to use. And you may think it would save you from targeting a multimodal target distribution, but our findings say that we have marginal improvements in the strongly log concave case, which was when we found this optimal schedule that was not only one. But in general, we may have big issues and actually slow convergence, even for cases where it was believed to perform well on. Interestingly, there was a concurrent work approximately at the same time as us. I don't know if Paula is going to talk about it later today, but of Go et al. That will also appear at ICLR 2025. They also consider the problem of quantifying the speed of convergence of Langevin algorithm when you use tempering strategies in the general case. But they have bounds that are worse in terms of epsilon. So it's a different strategy. And also they do not characterize this in terms of the functional inequalities or log Sobolev constants, but in terms of something that is called the action of the curve that basically tells you whether you moved horizontally one distribution to the other, which means that for people who are familiar with optimal transport, whether you had a small optimal transport cost within your interpolation. So this is one way to characterize as well whether your sequence of tempered sequences is actually good or not. Okay. If you have questions on this part, let me know. Otherwise, I will jump to the other one. Yeah.
So if you go to like your distribution, multimodal example. So this is bad it's bad for Langevin dynamics, I agree. But yes. For example, it's not just very important. So that you think that, for example, you did same stuff as sequential Monte Carlo, then the optimal schedules will be different.
Yes, it would be different because the analysis would be different and the convergence rates would be different. So yeah, instead of yeah, basically you can recycle a lot of things. Like you can use functional, like if you do sequential Monte Carlo, there's yeah, you're not really playing within the Wasserstein geometry, but more the Fischer-Rao one. So you would use functional inequalities that are suited to this geometry. But yeah, I think you could, in principle, recycle a lot of things that we did, but yeah, in another geometry. But yeah, it's a very good point. This example maybe would not be a problem for sequential Monte Carlo. Yeah, I don't know. I will need to study it. Thanks for the question. All right. So I have 10 minutes, 13. Yeah.
Yeah, 20 total.
Okay. Okay, so the second work I want to talk about today is also with Adrien Vachen, Omar Shehab. So it's this work is not published yet, it's on the archive. And the problem is still the same, but we use a different strategy for tempering. Let me give you some more details. So we still want to do sampling, so we still want to approximate mu star, okay, proportional to exponential minus v. And we want to solve this problem of sampling, like generate a sample of low p that is close to mu star, close in the sense of some divergence in epsilon, in the minimal amount of time. And minimal amount of time here is the computer science definition. We want a low complexity in terms of numbers of queries to the potential v. Okay, eventually to higher order derivatives, but in this work it will be a v. Okay, so this is how we characterize the complexity of the sampling problem. We've seen already what was Langevin EULA in discrete time. People have been using either this algorithm or since it's biased in the limit, which means that the law of this discretized process is not exactly mu star. They have also used an adjusted version that removes this bias due to the discrete time and the step size h. And this version is called MALA, or Metropolis Adjusted, which basically rejects from time to time some generated samples with probability encoded by the potential v. And we know that the complexities of these algorithms, so I showed in the previous part the rates in continuous time, for instance, for Langevin. They were very nice for v that were strongly convex. In discrete time, you need an additional assumption that is smoothness of the potential, which means that v has a Lipschitz gradient. And in this case, if you combine smoothness and strong convexity, you can get nice guarantees for EULA and closed algorithms. And when I say nice guarantees, it's that you have a nice dependence on the dimension, the condition number, and epsilon. Okay, so this is what we know in the nice case that is a strongly convex potentials and Lipschitz gradients. However, in practice, we consider often in Bayesian inference multimodal distributions mu star. So many real-life distributions do not satisfy this strong convexity assumption, which means that the potential would be like this, like a quadratic. So here in this work, we considered some relaxation that I've mentioned before. That is this strong dissipativity, which means being strongly log concave outside of some ball. Okay, so here, for instance, it's the same example as before. I have a mixture of Gaussian. The potential associated to it looks like this, and I see that it's strongly convex outside of some ball -4,4 in 1D. Okay, so it's already a relaxation, and it can capture at least more realistic distributions of interest. But the issue, yes, the issue is that if you assume such assumptions, actually the theoretical bounds for Langevin worsen a lot with the size of the ball. So here, or L is my smoothness constant, or is the size of the ball outside which I am strongly convex, and I have this exponential dependency, which is very bad. Okay, this is true for MALA as well. So we know in theory that the bounds get really worse in this case compared to the strongly convex case. And also in practice, we know that we have the same metastability issue for Langevin, which means that even with this, in these cases, I still have this multimodality. So in practice, Langevin gets stuck in a mode in practice, okay, for a very long time. Okay, so our question was the following. We wanted to know whether we could sample from multimodal distribution in polynomial time. Okay, so we want to avoid this exponential of the size of the ball. Can we do it, but with not Langevin algorithm, but something different? So what we do is summarize in this slide. We will need some assumption on the distribution. They will rely on the smoothness assumption, and I will explain what is this semi-log concavity along the heat flow, which is related to Langevin. Then we can exhibit a polynomial time algorithm, which is actually based on diffusion, so it's a small spoiler. And we will show that strongly dissipative distributions satisfy this mystical condition I've just shown before, and that hence we can sample from them in polynomial time, not like Langevin. All right, so I'm a bit short in time. I just want to mention that there was a recent work by Martin Czak that also derived a very nice bound, so polynomial bounds for similar distribution as ours that are strongly convex outside of a ball. But to achieve it, it relies on an important sampling approach. Okay, that yeah, if you have questions, I can comment on it, but I'm a bit short in time. So our method is quite different. In our case, we rely on reverse diffusions. So you may have heard about them for generative modeling. Here, we will use them for Bayesian inference. What these reverse diffusions do, they do the following. We want to sample from U star, okay? I will consider a forward process that is actually EULA, but initialized at mu star and targeting a standard Gaussian pi. Okay, so this is my grad log pi for a standard Gaussian. And I will denote the marginals PTV. Now that I have destroyed my initial distribution mu star through this process, I can consider the backward process that is written YT, that if initialized at PT, so it should be PTV, or big T, that is the end of somehow of this forward process, I can run it backward. And basically, this will generate a sample from U star. Okay. So intuitively, what this process does, it's also a kind of tempering, but it's not a geometric sequence as I showed between mu star and pi. They actually draw an interpolation of measures that are written as a convolution between pi and mu star. So I'm sorry, this is at the bottom of the screen, so I guess you see nothing. So mu t, so PTV, sorry, the marginals of my forward and backward process as well are actually a convolution between pi and mu star. And actually, this will be much nicer than the geometric strategy. Okay. In practice, you need to, we don't know what is P big T, so we need to initialize this backward process from pi that is the standard Gaussian, so there is a small error. The intermediate scores that are needed in the backward process are unknown, which are this grad log PTV, that is this, depending on the densities of my forward process, so I need to estimate them with some proxy estimator ST, and I need to discretize in time. Okay, so this is summarized here. I start from pi, I replace with the score estimator, and this is, I have a time discretization. Fortunately for us, we have access to some bounds that characterize how fast these algorithms converge to the target mu star. Okay, so here it's in terms of the reverse KN. And basically, under some mild assumptions on mu star, if I have nice scores estimators, which means that the L2 error in the marginals of my process between the true scores that I don't know and the estimators are bounded, then I can get a bound depending on basically dimension, quantities, fixed quantities with respect to mu star, the score estimation error, and this is just related to time and number of time discretization. Okay, so we have access to this from Chen et al. There are other papers deriving such bounds, but people were interested in this for generative modeling. Okay, they wanted to know if I have a good neural network and I generate good images, and they tried to explain it with such bounds. So in generative modeling, people have estimated these scores because with score matching, which is possible because you have access to samples xi through images from your data distribution mu star, and they use neural networks for that. In our case, we are doing Bayesian inference. So I know that mu star is proportional to exponential minus v, but I have access to no samples, so I cannot do score matching. So I cannot do, yeah, like in generative modeling. However, the scores are available in closed form, which is what I show here. Actually, there are two formulas represented by these two bullet points. And there are several papers that use the first one. And for now, there is, for the second one, I think there's only one paper and one that I cite in the very end of Tara Kutsage. So these two formulas basically are explicit formulas for these intermediate scores that you need to run the process. The problem with the first one is that it's a formula that writes with respect to expectation of these densities QTZ that are perturbed version of mu star. Okay, so this is my mu star, exponential minus v, and here I have a quadratic penalization. So at each time that I want to evaluate this guy for each point z at each time, I need to solve a sampling problem. So it's very heavy. But there are a few papers that did this, like even accepted at iClear and so on. It's a relatively heavy machinery, but people have considered it. And they use these formulas. Regarding the theory, the results are either incomplete or quite poor for the convergence, and it relates to characterizing how good these distributions are in terms of strong convexity as well. In our case, we use this formula. The difference is that it writes as a ratio of expectation. These expectations, the nice thing is that they are with respect to Gaussian variables, so it's very easy to approximate with Monte Carlo, but it's a ratio of expectation, so you may expect a high variance. Okay, I'm very late, sorry. So this is what we do in practice. We say, okay, this is my score estimator. I do Monte Carlo with Gaussian samples, and this is my score estimator. And I can use it along my reverse diffusion scheme to sample from mu star. So yeah, so this estimator, we can show, like, the trick in our analysis and in practice as well is that you use the same estimators for the numerator and denominator. This enables you to say that the score estimator is bounded. And so our goal in our life in this paper is to bound the L2 error of the score estimation. Okay, so I showed previously the bounds of Chen et al., people who had characterized the error of convergence for diffusion model. This was the key quantity, how well your score estimator approximates the true scores in L2 error. Okay, so this is an expectation with respect to the marginals. So this is what we do. And so I will be very fast on the results, but basically what we need to assume are some regularity conditions on the Hessian of the densities, log densities of the forward process, and some smoothness for the target density. This is a mild assumption on it. Finite second moment of M, and we are able to give a precise bound on this core estimation error, which is the key quantity. This bound, from your point of view, it must be very ugly, but basically it's very precise in terms of the dimension, number of samples n, the score estimator, smoothness constant, beta that we use for this regularity as well, and that's it basically. And since we have, so this was the main difficult work, and then we can plug it in the bound of Chen et al. And the nice result is that we have this final bound in the end. We can say that we can sample from, so this should be mu star, sorry, the target distribution up to precision epsilon in time, which means complexity, number of queries to the potential V, that is polynomial in all the constants of the problem, dimension, smoothness, second moment, and so on. So we were very happy with that because we don't have this exponential L R square. That was the size of the ball out of which we are convex. So I have not the time to talk about the proof, but if you have questions later, I can discuss it. And yeah, in the end, we apply this result to this strong dissipative distribution that are strongly convex outside of a ball. So this includes, for instance, some Gaussian mixture. And this is, in one word, we have this kind of complexities, which are so polynomial in R. And we are able to do this because we can characterize the regularity of the forward process. Sorry? Okay. Yeah, but I'm basically done. So first part of the slide say, okay, I have these densities of my forward process that are this PTV. I can characterize, so they have a potential associated to it. I can characterize if they are regular, which is this bound. And then using that, we are able to recover this polynomial complexity. Okay, so this is a very simple numerical illustration of target samples here on the left, what EULA would give to you. So EULA is this direct forward process targeting U star. You have this issue of missing some modes of the target, and this is what you get with reverse diffusion using our very simple estimator. Okay. So to conclude, so what we did in this work was to go to pursue the direction that people had started in generative modeling, saying that reverse diffusion are sampling algorithms that enable you to sample from some complicated distribution precisely if you can estimate the score precisely along the forward process. So this is exactly what we apply here. What I didn't really detail, but I mentioned, is that the key quantities we needed to control in our case are related to the regularity of the forward process. And the regularity means that these marginals are semilog concave, which means that I could bound the Hessian of this log PTV. So since we obtain this polynomial bounds, it means that we can sample efficiently even in these multimodal settings. So this opens a perspective for sampling for very complicated distributions with this kind of reverse diffusions, even in the Bayesian setting. And for the theory and numerics, our work is incomplete in the sense that we rely on these Monte Carlo estimators. They are efficient in a small dimension because we were polynomial, but still we had some d to the power 7 or something. And actually, you could imagine some algorithm where you use a neural network along the scheme to reduce the variance and learn better, which is close to what this paper does. And yeah. And also, I want to mention the recent work of Andrew, Dennis, and Paula. I don't know if Paula will talk about it later today, but that is very closely related to what I presented here, which means they want to characterize the efficiency of sampling algorithms with this kind of interpolation that are given by forward diffusions. And they consider close assumption to ours, except that they replace the semilog concavity with a moment assumption. But they also obtain polynomial bounds with respect to the problem. So thank you for your attention.
Have, for instance, a Markov structure, and we get a state space model. So I'm just trying to say that there are lots of stuff that have this sort of structure, okay? And lots of problem like this. Okay, so our task is to infer this latent variable x, and the approach we're going to follow is this empirical Bayes. So what's that? So our model has a parameter, so this theta. So first of all, we want to select a parameter, and we are going to pick the parameter that maximizes the likelihood of observing the data we actually observe. So this theta star that is maximizing the likelihood once we integrate away the latent variable because we don't observe them. And this is called the maximum marginal likelihood estimator. I'm just going to say MLE. And then we're going to take this theta star and plug it into this posterior distribution of the latent variable given the observations. And I'm calling this optimal posterior by abusing terminology, sorry. But yes, so we want to find this MLE and this optimal posterior to enact this empirical Bayes approach. Let me also say that we don't have to do this. Sometimes actually people only care about the MLE and not this other guy. But whatever, so this is, let's say this is the approach. And so the problem is that this is a very complicated problem because this integral here is often intractable, especially when the latent variables are highly dimensional. And even if it was tractable, this maximization could be very, very complicated. And actually also the posterior distribution might be intractable. So this is a complicated problem. And say the foundational method to solve this problem is probably the EM algorithm. that does something like this. So we start from a guess of the MLE and the optimal posterior, and we iterate these two operations. The M step, in which we have to solve this maximization problem, and then the E step, where we set our estimate for the optimal posterior to this posterior distribution, and we iterate. And in this talk, we are also interested in obtaining explicit error bounds for EM to the MLE and to the optimal posterior. So let me also say that EM is a very old algorithm. So you will think that we pretty much understand everything about EM. So this surprisingly is not the case, because non-asymptotic theory for EM is really not much. And let me also argue why it's not a completely obvious problem, because so for instance, take the theta. So this theta is obtained by maximizing this expectation, which depends on the previous value. But so it's a result of an maximization problem. So it's a very non-local move. It could be anywhere. Okay. So there's a crucial observation in this talk. This is a very famous result by Neil and Hinton. And it's a connection with optimization that basically is going to allow us to use lots of optimization-related, gradient flow-related techniques. So this result is saying that EM is actually a coordinate-wise minimization procedure on a space that is the product between the Euclidean and the space of probability measures of a free energy functional that I've written down here. Okay. So what does this mean? So this means that basically whenever we are doing the M step, so whenever we are computing theta, we are minimizing this functional in the first coordinate given the second. And whenever we are doing the E step, we are actually minimizing this free energy function in the second variable given the first. Okay, so we are alternating minimization procedure on the free energy. Okay. So now EM is a optimization problem on a very complicated space, because it's the product between the Euclidean and the space of probability measures. So we cannot really imagine, picture what the EM is doing in the space, right? Because it's a very complicated space to imagine, but we can at least get some intuition by pretending we know what's going on. So this is a plot for a coordinate-wise minimization on a function on R2. So R times R. So this is basically the M steps point are the points that minimize the function in the first variable given the second. And the E steps are the point that minimize the function in the second variable given the first. Okay, so this is precise. So what EM is doing basically, more or less, is that we start here and then we go to the red line, so which is we are doing the M step, and then we go to the blue line, and then we basically zigzag through the red and blue lines to the minimum of the function. Okay, so this is so this on the y-axis there is the space of probability measure that is not really this one, right? So this is just to get some intuition, and yes, so EM is doing something like this. Okay, so now I'm going to show you results for EM, but also for other algorithms. And so now I want to introduce some other algorithms, and the guiding principle will be this key message from Adams, Kwan, and Jennings paper. So we don't have to optimize the free energy like that. So EM is a particular optimization strategy on the free energy, coordinate-wise minimization, okay? But we don't have to do this, right? So if we can do this, well, it's amazing, because as this plot is suggesting, so this is a very quick way of going to the minima. But maybe we cannot do this, because we start here, and actually we don't know where the red line is, so we cannot perform the M step, or maybe we cannot perform the E step, right? So we want to find the alternatives. And so, for instance, we can think about this, the following optimization schemes. So EM is minimizing in the first coordinate and then also in the second, okay? an alternative when the M step is not available is to do a gradient step in the first coordinate and a minimization in the second. Okay, and then an alternative again is to minimize in the first and do a gradient step in the second. Now it's a gradient step in the space of probability measures. And now another alternative is just to alternate gradient steps. And another alternative again is to do just a big gradient step at once, okay?
Quick question.
Yeah.
What's the difference between the last two?
Yeah, so here, so it's gonna be clearer in a picture in a second. But basically in this case, we are doing coordinate-wise gradient descent. And here, not coordinate-wise, just, so it's a function of variable and we just do it all together, okay? So in a picture, it's gonna be clearer. Okay, so this is a picture for the first alternative. So here we cannot do the M step, so we take a gradient step instead, but we can do the E step. So this is called the gradient M, is something well known in statistics for a while. So we start here, we cannot reach to the M line, but we go at least into the right direction because it's a gradient step. So as long as the gradient step is not too big in a sense, we go into the right direction and then we do the E step and then we zigzag to the minima like this. Okay, so this is the first alternative. And now is the complementary setting. So now we can do the M step, but we cannot do the E step. And we take a gradient step in the space of probability measures. So I'm not gonna go into the super details now, but so in the E step is basically setting the posterior equal to this quantity, right? Here we are setting the posterior equal to the low of a Langevin diffusion, Langevin step, with that as an invariant distribution, okay? So in a sense, we are going still into the right direction. And this is what a gradient step in the space of probability measures looks like. And this is graphically is like this. And so this, we call this Langevin EM, but so it looks like a strange thing because you're setting this thing to equal to the low of a Langevin diffusion. But you can see this as a sort of limiting Markov chain Monte Carlo EM. Okay, so you're approximating the E step with many Langevin samples. Okay, and so this is a minimization gradient algorithm, and now we can do both things. We can just alternate gradient steps. So now the picture looks a bit like this with these many steps. And this is a mean field limit of the Soul algorithm of de Bortoli et al. So this is the algorithm. And okay, so there's now the alternative to this. So this is the difference. So now, so EM is a minimization algorithm on this space. The product between Euclidean and the space of probability distributions. So this guy has actually a Riemannian structure, and you can endow it with the geometry induced by the product of the Euclidean and the Wasserstein-2 geometry. So it has a geometry. You can make sense of gradients. You can make sense of a gradient flow, and you can make sense of a gradient algorithm. It looks like this. So now we are not doing coordinate-wise movements. We are just cutting, it's just a gradient descent. So we are updating all at once, okay? So it looks like this. And this is a mean field limit of particle gradient descent of Kunz et al. Or interacting particle Langevin algorithm. And so yes, so looking at the pictures now, we realize that EM looks very fast, right? And then this one must be a bit slower than EM. This must also be a bit slower than EM. This must be even slower than any of the previous. And then there is also this one that must be also slower, but it's unclear the relationship with this, right? But
why is the last one? Why must it be slower?
The
step size, or?
No, because so it's slower than EM because in a sense EM is minimizing.
It's slower than the coordinate-wise.
No, I'm saying so it's unclear if this is slower than this a priori. Okay, but we will get there. Yeah. So, but obviously these two guys that are maybe the slowest between the algorithms are also the most implementable, right? So you can implement this when both M steps and these steps are not implementable, right? Okay, so we have lots of tools to optimize the free energy now. And now we want to investigate all these sort of algorithms. And okay, so all of these algorithms are minimizing the free energy in lots of different ways, right? So to understand their convergence, in a sense, we need to understand how the free energy is changing throughout the iteration, right? So we need to quantify how much free energy we are losing across the iterations of the algorithms. So, okay, so now we will introduce a fundamental functional inequality that basically characterizes the convergence of all these schemes and which relates the free energy with this gradient. Okay, so we introduced this guy, so this functional I, given by this expression, you don't have to remember. And so this guy has an interpretation because actually it's the square norm of the gradient of the free energy when you endow this product space with the geometry induced by the product of Euclidean and the Wasserstein-2 geometry. So you remember I told you that this space has a geometry structure. You can make sense, at least formally, of gradients. So you can make sense of gradients and the square norm of a gradient, okay? And so it looks like this. And now we come to this fundamental functional inequalities I'm talking about, so which is also the log Sobolev of the title. Okay, so let me read it. So the statistical model, we say that a statistical model satisfies this extended log Sobolev inequality with a constant lambda if this inequality holds true. So yes, so this is relating the free energy to I, which is the square norm of the gradient. So what does this inequality says? That, so in a sense, the gradient of the free energy grows at least quadratically away from the minimizers of the free energy. So in a sense, when we are close to the minimizers of the free energy is very steep, in a sense. So it's a sort of intuition, but it's not really like that because it's a very hard space to imagine, obviously. But I mean, we want to think about at this condition like that. So this condition is very important for, so this functional inequality will regulate actually the convergence of all these sort of EM and blah, blah, blah. So let me do a couple of remarks now. So first of all, I want to justify the name. So in a sense, if our parameter space had only one element, so in a sense, if this the dimension of the parameter space was 0, okay, so this is heuristics at least. So this will be the log Sobolev inequality actually, that also Anna talked about earlier, which looks like this for the posterior distribution. And in a complementary setting, if the space of probability measures had only one element equal to the posterior distribution, this would actually be the Polyak-Lovacevic inequality of optimization, which looks like for the marginal likelihood, which looks like this. So in a sense, this extended log Sobolev inequality collapses to these two fundamental functional inequalities for gradient flows, right? Okay, so now a remark that is kind of, I mean, in a sense, I already said something like that, but I like to say it, okay? So this log Sobolev inequality is actually a property of a single probability distribution. Okay, we say that a probability distribution satisfies the log Sobolev inequality if this is the case. And this Polyak-Lovacevic inequality is a property of a function. Whereas our extended log Sobolev inequality, I don't like the name anymore, by the way, is actually a property of a statistical model. So it's a property of a family, parametric family of distributions, okay? Okay. Okay, so now we introduce this fundamental inequality, and now I want to introduce a couple of extra assumptions that we will consider together or separately very soon. So just smoothness, okay? So we say that the model is L theta smooth if it's the log likelihood is smooth in theta with the parameter L theta, and Lx smooth if it's smooth in X, okay? Yes. Yes. That's, I think so. I think so. That's unclear. But for instance, for what we wanted to do, that condition wouldn't work. So, okay. Yes. So, oops. Okay. Okay. So Okay, so now EM. So we have everything we need now. So this is EM. So I'm recalling just the picture and the iterations of EM. And this is the result. So if the model satisfies the extended log Sobolev inequality and its gradient Lipschitz, then we have exponential contraction of EM's free energy. Okay, so the free energy along the EM iterate is contracting exponentially fast. So this is a strange bound and it's the hardest to comment. Okay, so the others will be easier. Okay, I'm telling this also to myself. And so what's going on? So you look at this and the first thing you think maybe is the resemblance with the Langevin Monte Carlo sort of bounds. And in which case this will be like a bias. So this is not a bias because obviously EM is not biased. Here we have an infima across some sequences that look like step sizes, but obviously there are no step sizes in EM. So this is just a parameter in the bound. Okay. So first of all, if you took the sequence equal to 0, you kill this guy completely, and but you don't kill the convergence rate. Okay. So this is not a bound, and you can do better than that. In a sense, what you really want to do is to take these step sizes to be as large as possible in the beginning and then small afterwards in the bound. And if you do that, you get something that is just little o of this rate, okay? Just to have something more easier to look at, okay? Okay, but I stress again, this is not the step size because there are no step sizes in EM, but it looks a lot like the step size in Langevin Monte Carlo. I mean, it's not happening by chance, obviously. Okay, let me also say that we can also actually have the smoothness in X to fail. So it doesn't have to be smooth in X. In this case, we get a slightly worse rate, okay? No, I mean, it's big O of that, and this is small O of that. Then it's unclear how much worse. Okay, so now we understood that under the extended log Sobolev inequality, we have this fast contraction of free energy, but this is not what we were after anyway, right? So we actually wanted to deduce convergence of the iterates to the MLE and the optimal posterior, right? That's what that was our goal. So we will do that now. And to do that, we consider another functional inequality that has a very deep connection with the gradient flow stuff, which is this one. So in this functional inequalities, we are relating the metric distance of a point theta q in the space to the minimizers of the free energy, like that. And so why is this inequality cool to have? Because basically, whenever then we have a bound in free energy, we immediately get a bound in a metric distance, okay? So it will be very cool and very useful to have. And okay, so there's a very deep connection between this inequality and the extended log Sobolev inequality. And this is a generalization of Otto-Villani theorem. I could call it the extended log Otto-Villani theorem. So if the model satisfies the extended log Sobolev inequality with a constant lambda, then this other inequality will also hold with the same constant lambda. I'm calling this extension of the Talagrand inequality because in the same way as the extended log Sobolev inequality generalizes log Sobolev, this is generalizes Talagrand, okay? But it's precisely the same stuff. So now, so basically what this means is that whenever we are assuming the extended log Sobolev inequality, we get this for free. So actually we can immediately translate our bound in free energy with a metric bound, okay? So we have this the following non-asymptotic error bounds for EM, okay? Okay. So now we had some other algorithm to look at. And so this is the next one. So this is gradient EM. So here I remind you, we are taking a gradient step in the first coordinate and then a minimization step in the second for the free energy. So the picture is like this. And now we have that if the model satisfies the extended log Sobolev inequality, and we have this smoothness in theta with L theta, then if you choose the step size small enough, now there is a step size because it's a gradient algorithm, you have this the following bound for the free energy, for the metric distance of the iterates to the MLE and the optimal posterior. Okay, So just to remind you, so obviously this in this plot we see that this looked a bit slower than EM, right? And in EM, basically we have this little o of this rate, okay? And here we have precisely big O of that rate, right? So it's we discovered that actually EM might be faster than that, as we obviously would suspect. And now we have this the complementary setting where we actually take a gradient step in the second coordinate. It looks like this. So the name is Langevin EM. And again, if we have the Alexander-Loxoblev inequality and we have smoothness in the x coordinate now, we have the following non-asymptotic bound for the iterates. So now we do have a bias because basically the forward discretization of the Langevin diffusion is biased. And the H here is the step size. And in a sense, so I'm not expecting you to completely follow me now, but if you look at this bound for Langevin EM and you look at the bound for gradient EM, okay, so there are this and this, and then we look at the bound for EM, EM's bound is like the best possible way of combining the two bounds, okay? In a sense, okay? So you can also just ignore the thing I just said. If it's not making sense. Then we had this alternative. So this is the most implementable scheme so far. So coordinate-wise gradient descent. So now, if again the model satisfies the extended Loxoblev inequality, and now we want smoothness in both coordinates, then if we choose the step size small enough, and now we are using the biggest Lipschitz constant, okay? We have this non-asymptotic bound, which is worse than any of the bounds we derived before, okay? And okay, so now we also have one last algorithm, which is this one. And we have a similar conclusion, apparently similar conclusion. So if the model satisfies the extended Loxoblev inequality, and we take the step size small enough, we have a bound that is basically identical. So the difference here is that we have to take the step size to be smaller than 1/4 times the biggest Lipschitz constant, whereas in this one, 1/8. Okay, so in a sense, for this one, we can take the step size to be bigger. So basically, we are gonna converge faster for the same bias. So in a sense, this is suggesting that this algorithm is faster than than the previous one. So the picture also sort of suggests this. So is this always necessarily true? So I think most of the time, yes. So it's important to notice that here we are taking the step size to be the same in both coordinates, okay? So in a sense, you need to be extra careful here at every iteration you do in order to not overshoot because you're using the same step size. But in this algorithm, you can also choose different step sizes for both coordinates. So maybe, I think in some situation, you can get actually this algorithm to be faster, but it's unclear. Okay, so now, so what did we find out so far? So we discovered that this fundamental functional inequality is able to characterize the fast convergence of EM and all these other variations. But so it's a very strange condition because it's a gradient condition on the free energy with the square gradient of its square gradient of the free energy in this abstract geometry. So it's a very nasty condition, right? So it's unclear what this means. And obviously we want to be able to verify this condition. So when does this extended Loxoblev inequality actually hold in practice, right? So we want to answer these sort of questions now. Now we have a result that we might as well call the extended Bakry-Emery theorem. So basically, this is telling us that whenever our log likelihood is strongly log concave, then automatically we have the extended Loxoblev inequality. Okay, so in a sense, so it's a stricter relaxation of a strong concavity, as we would expect. Because in a sense, the Loxoblev inequality is a strict relaxation of strong convexity of the potential, and also the Polyakov-Vasevich inequality, right? So, which are like the marginal functional inequalities for the extended Loxoblev inequality. So we also have a result like this. And if we come back to our hierarchical model, so we had a situation like this. And so now, for instance, whenever we know that whenever this parameterized function and these probability distributions are gradient Lipschitz and strongly log concave, then this hierarchical model will return an EM that is converging fast. Okay, I mean EM applied to this problem will converge fast, and also all the others. And also an example I didn't type down, but also a Bayesian logistic regression model considered in the Bortoli et al. Or Kunz et al. Also satisfies the condition, so we have fast convergence also in those cases. And okay, so now, I'm going to present a result that maybe is not in the most useful form already, but it's just trying to make a point related to something I just mentioned actually. So for the log-Sobolev inequality, there are lots of results like this. So if we have a probability distribution that has this log-Sobolev property, then if we do something to this probability distribution, like if we perturb it, we do stuff, okay, we do mixers and stuff, then this bounded perturbation, this perturbation will also have this log-Sobolev inequality property, okay? And this sort of results is fundamental in the literature because it really shows how powerful this inequality is. And yeah, it's at the center of lots of research, right? So obviously it's natural to wonder if we have this sort of result in our setting. And so now I'm presenting something like that. So we have something like this, for instance. So for the extended log-Sobolev inequality, so suppose that we have a model that satisfies the extended log-Sobolev inequality with a constant lambda. And then we take another model where the marginal likelihood is the same, but this conditional distribution is different, okay? So that's called the completion in EM sort of things. And this completion is a bounded perturbation of the original one, in the sense that it's a bounded perturbation, like the densities are upper and lower bounded like that. And then the gradients of this these two distributions are in theta are the same around the MLE, and away from the MLE are not too far. Okay, so in a sense, it's a bounded perturbation of that, and then we have that this perturbed model also satisfies the extended log-Sobolev inequality with some constant. Okay, so all of this can be made a little bit more precise. So what do I want to say with this result? So first of all, I want to say that this shows that there are models for which the log likelihood is not concave, and still the extended log-Sobolev inequality holds. Because suppose I start from a strongly log concave model, in which case I know that the extended log-Sobolev inequality holds because we had this Bakri-Emery type result. And then we consider this a perturbation far away enough from the MLE in a way that is non-concave. Okay, maybe just around 1 point, okay? And then this model is obviously non-concave, but still will satisfy the extended log-Sobolev inequality. And so EM will be fast and everything, okay? And there is also a very interesting relationship with the choice of completions in EM. So often when you do EM, you have this marginal likelihood here, something like that, that you want to maximize, but you choose the completion, okay? So you create like an artificial model, okay, to get, and when you do that, what you really want to do is to get EM to converge fast, okay? So the choice of the completion is is like the key element, right? And here, with this sort of result, we are saying, we are basically comparing what happens to EM when we change completions, right? Because the extended log-Sobolev inequality dictates the speed of convergence of EM. And let me also say another one last thing, since I'm almost done. I have some minutes. So yes, I said that as under the extended log-Sobolev inequality, EMs contracts fast, and this log-Sobolev inequality is sort of regulating the speed of EM. We also have a sort of natural interpretation of the log-Sobolev constant, because in a sense is the maximum ratio between sort of free energy, so like entropy and information that is produced along EM. Okay, so there is also a sort of natural interpretation of the convergence constant. Okay, so think I'm all basically done. So, okay, so I will just gonna wrap up. Okay, so I've shown you the non-asymptotic error bounds for YAM and related optimization schemes. And I think one of the best things, one of the things I like the most is that the proofs are somehow a generalization of the finite dimensional arguments. And they're also very easy, I think. So the YAM proof is very, very quick. And I think this is good also when you want to generalize this sort of arguments. So we like that. And also, we also like the connection between YAM and this increasingly popular of Wasserstein gradient flows and the fundamental functional inequalities. So I think probably the most important things are not the result themselves, but the strong suggestion that techniques from the functional inequalities literature can be used to understand YAM. Okay, so I think that's the most important point, aside from any sort of non-asymptotic result. And I repeat, so there's really not much on asymptotic analysis of YAM. So we feel like this is cool. Yes, we are currently looking at a number of follow-ups. So you should get in touch if you're interested. Please do get in touch. And yes, thank you.
Gradient flows on the maximum mean discrepancy. How am I going to structure this talk? First of all, I'm just going to give like a very quick overview of what the MMD is. It's a divergence measure on probabilities. It's an integral probability metric. And we're going to sort of see what it looks like in a fairly concise sort of way. We're going to then connect this statistic with the problem of training neural nets. So this is a reason for studying gradient flows on MMD, is that it actually looks a little bit like the kind of optimization you might do when you train a neural net. That might not make sense yet, but it will hopefully make sense after I've gone into more detail. Then I'm going to talk about Wasserstein gradient flow in the MMD. So this is using this MMD as a loss when you're optimizing over probabilities. Then I'm going to talk about two different ways of helping this to converge to the right answer. One of which was in our original paper. It's a noise injection approach. And then the second, more recent approach is adaptivity. So it's not that you have a single divergence, but you have a whole family of divergence, and you choose among them in order to make convergence happen. All right. So yeah, these are the two papers that it's based on. So why study gradient flow on MMD? One reason, which was actually the reason that motivated us initially, is to understand GANs better. So if you have a generative adversarial net, you have a critic, which tells you how far away your distribution is from its target. And then you have a generator, which is generating new samples. And you're basically alternating between improving your critic and improving your generator until your generator generates samples from the target. So what we thought was, well, you know, why study this very complicated system when we can study a simpler one? Throw away the generator. Replace the generator with a set of particles and just have a critic. Okay, and then, you know, it might be easier to study the convergence of this system, which is just using a critic, an adaptive critic function, in order to move particles around. Okay, so this is actually what motivated us. And then subsequently, we saw this paper which sort of took this distributional perspective on training neural nets. And then this led us to also realize that what we were doing was useful for that setting as well. All right. So brief introduction to the MMD and MMD flow. All right. So the MMD is an integral probability metric. It's a measure of difference between distributions. So in this case, I always have distributions P and Q, where P is blue and Q is red. So I'm looking for a well-behaved function that maximizes the difference in expectations under P and Q. So this is true for any integral probability metric. So this is true for Wasserstein distance and so on. Functions of bounded variation 1 give a valid critic as well. In this case, my class of functions is going to be a very simple class of functions. They're going to be functions that can be written as linear combinations of features. Okay, so phi of x are features of x, and f are the coefficients that cause that linear combination. Now, where things might get complicated is that I might have infinite feature dictionaries. And in fact, for many cases of interest, I will have infinite feature dictionaries. So this is fine, as long as whatever method that we use in the end only depends on the dot products of those features. And if we have the dot products in closed form, and our algorithm only depends on dot products, doesn't matter if I've got infinite feature dictionaries, because I can still manipulate them via their dot products. Okay, so here's just an example. In this case, I've got blue is Laplace, red is Gaussian, and this here, this f in green is my witness function. I'm going to call it a witness function. This is a function with sort of largest amplitude, where the difference in mass is greatest, subject to it being smooth. So I'm sort of saying my function is a linear combination of features. These features are sort of generically smooth, and so I'm going to end up with a smooth function. All right. So that's the maximum mean discrepancy, but I need to express it in terms of kernel functions, because if I can't do that, then I can't use these infinite feature dictionaries. All right. I should emphasize here that, this is one among many integral probability metrics. So the Kolmogorov metric is a valid metric as well. That's the largest difference between CDFs. That can be computed as an IPM using functions of bounded variation 1. The Wasserstein distances use bounded Lipschitz functions. So you can use many different function classes here. We are using a specific one, which is an RKHS, reproducing kernel Hilbert space. All right, so how can we now express the MMD in terms of kernel functions? Well, here is our MMD from a couple of slides ago. Okay, difference in expected Fs. Now, because I'm in a Hilbert space, I can express this as the dot product of these coefficients and the difference in expected features. So what have I done? I've said the expectation of F is this dot product here. I've taken the expectation inside, which I'm allowed to do if my kernel is bounded, so a small technical condition. And then I've got these coefficients multiplied by my expected features under P. Okay, so fairly straightforward operation. So I've got this difference in expected features under P and Q times F. Now F is in a unit bowl. So that means that the F that maximizes this dot product is just the unit vector pointing in the direction mu P minus mu Q. If I take that dot product, then I get the norm of the difference of my features. Okay, so I have actually the solution of this optimization in closed form. So that's pretty nice. That means that I can compute the witness function purely in terms of dot products. Okay, so my witness function at x, I should say, is the dot product of mu p minus mu q and my features at x, which is basically my expected kernel under p and my expected kernel under q. Okay, so that this function from a couple of slides ago here, when I'm computing it at x, this is how I get it purely in terms of kernel functions. So no more infinite feature dictionaries. And then this statistic itself, I can also compute entirely in terms of kernels. All right. And so here we have a pretty nice intuition. So if you think of a kernel as a measure of similarity, so it's a dot product, so dot products are large, then the vectors are similar, then this is sort of the average similarity of blue to blue. This is average similarity of red to red, and this is minus the average similarity of blue to red multiplied by 2. So in other words, if blue is on average as similar to other blue points as they are to red points, and likewise red is as similar to other red as it is to blue, then this whole thing goes to 0, and I find that P and Q are the same. Now, if my feature dictionary is rich enough, this quantity is going to be 0 if and only if P and Q are the same. And this is actually not too difficult property to achieve. So if you're using, let's say, a Gaussian kernel, then this will be true. Okay, so that's the crash course on MMD. Any questions about that before I go on? Great, no questions. Good. Okay, so we've introduced the MMD. Now let's define a gradient flow. So this paper appeared in Europe's 2019. So Michael Arbel, Anna Korba, who is here, and Nadil Salim are authors of this work. All right. So one way to motivate this, and this is the connection I spoke briefly about at the start of the talk, is in respect of neural net training. Okay, so let's say that we have a neural net, and it's going to be a fairly simple neural net here, where I've got like a bunch of neurons, so it's just a one layer neuron. Each of these neurons has a parameter zi, and then all of these weights are 1 on n. Okay, so the final weights are all 1 on n. So I've got this sort of average of my neurons with parameter zi evaluated at some x. Okay, and what I want to do here is I want to minimize the squared loss between this function, this neural net function, and an output y. Okay, so I've got a squared loss here. Okay. Now, if I'm minimizing this loss, what I would do is something like gradient descent, right? Where I would take the derivative with respect to each of my neurons' parameters of this loss function, And then I'd update those parameters from time t to time t plus 1 using this gradient descent step. Okay, so this is basic neural net optimization, one layer, and uniform final weights. What has this got to do with MMD, right? And gradient flow. So one thing we might think of is, well, let's imagine this neural net becomes infinitely wide. All right. And then we've got sort of infinitely many of these. And so we can sort of think, well, I've got more and more of these sort of particles, so to speak, which are the parameters of my individual neurons. Well, this is going to converge to some sort of distribution over neural net parameters. Okay. So my nu here, this letter here, represents the population version of these samples. So number of samples goes to infinity. All right. And then this loss here, where I had a sum over my neurons, turns into this expectation here where z is drawn from my distribution over neural net parameters. Okay, so I've gone from optimizing over a finite set of parameters here to a distribution over parameters there. All right, so we're getting closer to MMD, but then we're not quite there. Okay, this is from the previous slide, so I'm minimizing the squared loss between y and my expectation over z of my neural net features, where z are my neural net parameters. Now let's imagine that my target function can be written as the expectation over some distribution over parameters of my features. Okay, I don't know that, this new star, but I know that my function is well specified. So the target is in the function class. All right, then this is what my loss looks like. So what I've done is I've replaced this y by its expectation under a new star of these features. And now this is my loss. Okay, so I just substituted this in. And now I do have something that looks like an MMD, right? It's an MMD where the kernel between a particular set of neural net parameters z and a particular set of target neural net parameters u is the expectation under my data distribution of the dot product of my features of x under u and under z. Okay, so this is a valid kernel, a valid measure of similarity of these parameters u to these parameters z. Now I've got an MMD. Any questions? All right, so now what we want to do is some sort of optimization over this distribution nu in order that it should approach this distribution nu star, and we're going to do that by minimizing the MMD between these distributions. All right, so let's start with an intuition, and then let's go to the math. So here is the intuition. So we're going to assume that our distributions are in the space where they've got bounded second moment. Okay, and now this is my loss function. I'm just dividing by 2 to make the math a little bit less crowded. And now I'm sort of thinking of this MMD in terms of a particle interaction formula. Okay. And so basically, like, blue are the particles that I'm optimizing, and I've got some distribution over these particles. Red are the target particles. Okay. And now one can sort of think of this term here as the average interaction force between 2 blue particles. So this is how blue particles are sort of repulsing each other. This term is a constant because it's a function of my target particles. So yeah, constant. And then this is a confinement term. So this is how, like, aggressively are red pulling blue towards the target. All right, and you can sort of see the signs are opposing here. So with this in mind, let's consider if I've got some particles yi drawn from nu star, some particles xi drawn from nu, what would be the force on an individual blue particle z? Okay, just one particle. So I'm just looking at the force that's being applied to that one particle. Okay, so I'm sort of using physics language here. So what it would be is, well, I'd just have this average repulsion force between my z's and all my other blue particles, and then I have the average attraction force between my z and my red particles. And looking at this and remembering what this witness function looked like from a few slides ago, this is just the gradient with respect to the coordinate z of this witness function. So remember a couple of slides ago, I'll just return to it. The witness function is expectation under P of my kernel minus expectation under Q of my kernel. I take the gradient of this with respect to this point here, and then this gives me the force on my individual particle X. And so this is what we've done. Okay. So this is physics. Now let's move to math, and let's formalize that this is indeed a correct thing to do if we're doing some sort of gradient descent on the measure nu in order to make it approach the measure nu star. So, you know, this is sort of fine as a sort of hand wavy thing, but now let's make it formal. All right. So Wasserstein gradient flows. So Wasserstein gradient flows are a gradient descent on the space of probabilities. So because we're working on the space of probabilities, we need some sort of metric in order to compute gradients. The metric we're going to use is the Wasserstein 2 distance. Okay. And we're going to basically minimize loss. We're going to do gradient descent on some loss, which is in our case the MMD, with respect to the Wasserstein 2 metric. Okay, so in the Wasserstein 2 space, what is the tangent space on our space of probability measures? Well, the tangent space is just the set of square integral functions. And if I move in a direction h in the tangent space by some distance epsilon, then I get this low-order Taylor expansion, right? So here is my function at the starting point. Here is the gradient of my function, my Wasserstein 2 gradient, dot producted with h, the direction that I'm moving in. I'm moving a direction epsilon, and then I've got some remainder term. Okay, so this is, you know, just standard gradient descent, but we're doing it in the space of probabilities with bounded second moment with respect to the Wasserstein 2 metric, which gives us this second order expansion. Okay, so this you should recognize as just being like a gradient descent, but I've now sort of led myself into some difficulties because I need this expression here, which is my Wasserstein 2 gradient of my MMD, and you know, how do I compute that? Okay, so there is a solution which is explained in this very nice book here, which is I can compute this Wasserstein 2 gradient. Okay. The way that I compute it is by taking the derivative of something called the first variation. So what is the first variation? If I start at a point mu, and then I perturb my density by an epsilon such that that perturbation remains a valid density. So that means that it has to basically like not integrate to anything other than 0. So there's sort of a restriction on the kind of epsilons that I'm allowed to, size that I'm allowed to perturb my density with. Okay. So I can again do something that looks like a Taylor expansion with respect to this perturbation, okay, which is a perturbation that keeps mu in the space of probabilities. Then the derivative of this expression here gives me my Wasserstein 2 gradient, and then I'm done. So this gives me like a sort of simple algebra problem that I can solve in order to get something that turns into a Wasserstein 2 gradient. All right. Once I've got the Wasserstein 2 gradient, I can just define a gradient flow in the usual way, okay? Which is to say that the change in my measure here is given by the expression here in terms of the current value of the measure and the Wasserstein gradient flow. So this is like a completely standard expression for gradient flow, which generalizes the gradient flow in RD if you just have a function. Okay, so this is then, you know, once we have this Wasserstein gradient, this is how we update our probabilities using it. Like this is the stochastic this is the ordinary differential equation, I should say, that I'm following in order to update my probability. Okay, so these are the steps we need to follow. Now let's actually follow them for the MMD. Okay, what is the first variation of the MMD? Well, lucky for us, it's the witness function. Great. And so now here is the differential equation that we're going to follow when we, we do Wasserstein gradient descent on MMD, which is indeed a moving in the direction of the gradient of our witness function. Okay, so lucky for us, all of this sort of arrived at the point which is that we are using the gradient of the witness function to update our distributions in order to approach our target. Okay, so this is in terms of probabilities, but I need to implement this using particles, right? So how do I go from something on the space of probabilities to something I can implement with particles? Here is the particle version, which is like if I have a sample of particles from nu 0 and I want to move them according to this equation here, then this sort of, space discretization of my differential equation takes this form, where indeed I'm updating ZT using the gradient of my witness function. Okay, under some reasonable assumptions on the boundedness and differentiability of my kernel. So what we've now done is that we've formally arrived at the thing that a couple of slides ago I described by waving my hands. Any questions? Yep. Yeah. Yeah.
Were you relating it back to the Quantic case, or just were you relating it back to the Quantic case?
Yeah, so like what we're sort of interested in showing is that in the limit as the number of particles goes to infinity, that does, approach the continuous case. Yeah, that's right. So there are two discretizations. One is over space, so particles instead of measures, and then one is over time, which we're about to get to, yeah. So here is the time discretization, which is basically rather than having a continuous time differential equation, I'm now taking steps, okay? And so the steps that I would take using probability measures are basically these sort of discrete steps where I'm doing a push forward by the gradient of my witness function. And how does that look with particles? Well, it looks like this, where I'm moving my particle a small distance in the direction of the gradient of my witness. Okay, and we can sort of show that in the limit as the number of particles goes to infinity, as the step size goes to 0, that this thing here is going to approach the true gradient flow. Okay, that's fine, but we've glossed over actually a rather challenging question, which is that this particle flow, like Wasserstein gradient flow under MMD, does that actually mean that nu t converges to nu star? Let's find out. Okay, so one notion that is really helpful in determining if things converge is convexity, right? If I'm doing gradient descent or gradient flow on a convex function, then I know that I will hit my global solution. So what does convexity look like in the space of probabilities? Okay, for convexity to be defined in the space of probabilities, we need to first of all define a path between two probability measures. This path, geodesic, is given by the following, where I sort of start with an identity map, and as t increases, I sort of push forward between nu1 and nu2 using this transport map t. Okay, so this is like the path that one probability uses to move towards another probability. Okay, and a function is displacement convex if it is convex when my rho, my measure, moves on this path from nu1 to nu2. Okay, so it's this sort of convex property holds when I make this displacement along the path, along the geodesic. Okay, so graphically, what does that look like? So here I'm moving my blue along such a path to my red, and you can see this blue bump sort of shifts to the right in a nice way. Okay, now sad to say, MMD is not displacement convex. So MMD does not satisfy that property. So we can't just snap our fingers and say, well, because this holds, then we get convergence. Okay, MMD actually is convex in a very annoying way, which is basically like teleportation convex, which is to say that if I took my mass from my blue and teleported it to my red, then it would be convex under that mapping. But so what, right? Yeah, not useful. Okay, so that's very sad. So we are going to make a modification to the MMD flow under which modification we can say something at least about convergence. Okay, so here is the modification that we're going to make. We're going to sort of evaluate the gradient of our witness, not at the location of the particle that we're moving, but near the location of the particle that we're moving. Okay, so here is the location of the particle we're moving. I displace a small distance beta drawn by some, according to some noise distribution from that location, and then I evaluate my gradient there. So it's sort of not evaluating my gradient at the particle, but near the particle. Okay, so what you might then think is, well, is this the same as entropic regularization like you would use if you were doing a SDE version of a flow? No, it's not. If I was doing entropic regularization, I would be adding noise after computing the gradient. And this would add some bias, but it would not necessarily help me converge, okay? So you notice that what I'm doing is I'm adding this noise inside the witness function. So I'm evaluating the gradient close to, but not at my point, as opposed to taking my gradient and adding noise to it, which would be entropic regularization. Okay, so this is what we're doing. So if we do that, we need to figure out how much noise to add. And this isn't just a case of having like noise going to zero. It's a little bit more complicated. So you need noise that is small enough that you don't just evaluate somewhere random, but you need noise large enough that it actually makes a difference. And that trade-off is a little bit hard to actually achieve, but we do have conditions on it. So this is basically the small enough condition. So the amount of noise that you add should be small enough that you're getting this sort of descent property here that f is improving as I do my iterations. But it should be large enough that this squared sum converges to infinity. Okay, so subject to these two trade-offs being the case, then we get this nice result that my f is decreasing, so my MMD is decreasing in this way here. Okay, so this leaves open a little bit, you know, the problem of designing in practice this beta schedule, but this at least gives a circumstance under which we get convergence. All right, so now let's look at what this looks like using some simulations in 2D. So here is a set of data points, and the arrows here are the gradient field being applied to them when I'm evaluating not at the particles, but near the particles in the way that I described. Okay, and here is my target distribution. And what you can see here is that the particles do indeed flow towards the target. Okay, high-tech animation. Yeah, right. So yeah, so this does seem to work, you know, modulo designing the beta schedule in a reasonable way. Yep. Yep.
So does it not work the same way without the betas?
So I do have actually, so without the betas, it doesn't work terribly well. What happens is that you kind of get a situation where you've got, on one hand, I'll just draw it here, you get a lot of particles. Oops, actually, I'll use a different color so you can actually see it. I'll use orange and a thick pen. Yeah, so you get on one hand, a lot of the blue particles are sort of converged in a ball here, like all in the same place. And then you get a few orphans out here that aren't moving. Yeah. So yeah, we're using Gaussian noise to perturb the particles. Yep. So indeed, it's kind of like we're smoothing this thing, which we are going to come to, which was the insight we started using for the next bit. Too fast. Yeah. Yep. Yeah. So I think if you were, so the beta trick is, would you need the betas? I think you would still need to adapt your divergence in a way that I will describe. Yeah. Because you can verge up to a boundary, right? I mean, yeah. Mm-hmm.
As soon as we are in finite particles, it's so.
Yeah.
For an infinite number of particles, we could see something very
I mean, so we had, let me see if I can find it.
We cannot use convexity, but we have
So we had this. The issue was, though, that this required the negative Sobolev distance to be bounded. So it does converge in the population limit under a heroic assumption. Yeah. You know, it is a result, but it's a result that.
That's the h to the minus 1.
Yeah.
Oh, wow. Okay. Yeah. Okay. Gotcha.
On the support of Newton, Newton has support everywhere, in particular support everywhere. It can be satisfied, but if you have finite number of particles.
Gotcha.
Yeah. So yeah. Let's go back. Here we go. Yeah. Yeah, actually, I had also, in fact, I've got the picture of what the endpoint looks like, just to show you, indeed, like this is kind of what happens when you run it without the noise injection. So it's not, not great. But I think this insight that you had of adaptivity is a good one, and we will now approach that. Before we do, just to return to the training neural net example. So here is our neural net training example once again, where we've got our target function, which is a function of these u's here, and we're trying to optimize our z's so that these things match. Now, in this case, what we are seeing here, so this is like how many steps we've taken. This is the MMD to the target. And we've got a few traces here. So basically, this is just SGD without noise injection. This is what we get with noise injection, so obviously much better. What we do here is this entropic regularization. And entropic regularization actually isn't bad in the sense that it does sort of kick you out of local minima, but it adds a bias, and so there's a sort of floor that you reach that you don't improve over because you've sort of got this noise floor that you've added. Okay. And then this is an approach that's sort of similar or related to ours, which is called the Kernel-Sobolev discrepancy, which I will not go into detail on, but it's, not doing as well. All right. So now to this point of adaptivity. So you might think, well, if you're adding noise before computing the gradient, isn't this sort of like blurring your kernel function a little bit depending on the time? Which amounts to sort of using a different witness function kernel, in fact, over time. So we thought, well, maybe why don't we do that directly? So this part of the talk is going to be a little more applied, but I think it's an interesting topic for study. Yeah, this is a paper appearing at iClear, which we did at DeepMind recently. And this is with Alexandra and Valentin. So let's first of all address a case where we can actually do a proof of something. And then we're going to go into engineering land, okay? So where can we do a proof of something? So nu star is a Gaussian. That's our target, okay? Mu-t is a Gaussian with mean mu-t, okay? And mu-t we want to sort of push towards nu-t, okay? Very toy problem, okay? And we've got an MMD, but now the MMD doesn't have a kernel, but it has kernels plural, where the bandwidth of the kernel is alpha, okay? And so our goal is basically like we want this blue to sort of push towards the red and get closer and closer. We want to do gradient flow, Wasserstein gradient flow with MMD, but yeah, with respect to this single parameter here. So we're in a parametric family now. Okay, so it's actually not Wasserstein gradient flow, it's just, gradient flow, yeah, or gradient descent even, okay? So how do we choose our kernel in order that we go as quickly as possible to the target, right? The way that we would do it is we would choose an A star that for a given time maximizes the gradient with respect to the parameter we're adjusting of the MMD, right? Because if we do that, we are pulling to the target as fast as we can. All right. Now, because everything's Gaussian, kernels are Gaussian, distributions are Gaussian, we have a closed form expression for that. And what you can see is that as my as my blue goes towards my red, my bandwidth is going to go down. Okay, I'm getting a narrower and narrower kernel in order that I'm maximizing the pull of my gradient. So it's sort of like saying that as my distribution approaches the target, I should sort of look at the difference in these distributions at a finer and finer length scale in order to pull the distribution as fast as I can. Yep.
You said as fast as you can.
Yeah.
Can you say a bit more about that? How do you know that it's as fast as you possibly can?
So I'm just choosing the kernel that maximizes the gradient of this. Yeah. So like this gradient is telling me how quickly I'm moving this to its target. So if I'm maximizing the norm of the gradient, I'm moving mu-t as quickly as I can to the target. Yeah. Yeah, and you can see, so the kernel width is dropping as opposed to like a fixed kernel width, which is in orange here. But then this non-adaptive MMD, I mean, it converges to the target, right? The mu-t does converge to where it needs to go, but it does so much slower than I achieve when I use the adaptive kernel, which hits the target, here, and it's done. Yeah. Mm-hmm.
Apologies if this is a misunderstanding, but is it possible to overshoot?
So the gradient is going to vanish when my mu-t hits my mu-0. Yeah, and then I'm done. And in fact, at that point, the kernel also shrinks to 0. So there is no, there's no more signal, but there's no need for a signal. Yeah. Yeah. Cool. Any other questions? Okay.
I
Yep.
mean, in terms of the diagram, you showed the vectors going towards a point.
The other one, yeah. I mean, that's a little, in a sense, like here we have a much easier problem, right? Because here we have the whole density. So this is, I would say, you know, it's a case where we can prove that adapting the kernel is useful, but it's massively oversimplified as compared with the gradient flow on probabilities that I talked about earlier. So this is just to sort of say, well, here is a case which we can prove. Yeah. So I did warn you that the math was going to become less rigorous in the second part of the talk. So we're definitely in that territory now. Yeah. But, you know, nonetheless, you know, here is a case where we can show that adapting the kernel is helpful. Okay. So now a question might be, well, if I can do this for 2 Gaussians, great, fine, wonderful. But now I want to do it when I'm moving a bunch of particles, which might be in very high dimensional space. They might be images even. How do I find a sequence of MMDs that is the right sequence of MMDs to pull my samples towards the target? Okay, so this is what I'm going to describe next. And what we're going to do is we're going to use the technique of diffusion models in order to basically train our sequence of MMDs, which is going to be a lot of fun. Okay, so a quick reminder to everybody of diffusion models. So basically, diffusion models are a way to go from a set of clean samples to a Gaussian over some number of steps, which in practice, in principle, needs to be infinite, which is basically like I've got a noising process that takes my clean images and adds more and more noise until it turns into a Gaussian. And then I've got a parameterized denoising process that takes my noisy sample and progressively cleans it until I get a distribution over images. Okay? And it's this reverse direction that we're going to take advantage of in order to train a sequence of MMDs, which will be suited to moving particles to a target. All right. Okay. So I'm going to use a tilde to denote the samples that I'm taking from this noising process, as distinct from the non-tilde nu, which is what I'm going to actually be denoting to generate particles using the MMD flow. Okay, so these are just the training particles from my MMD as opposed to the particles later, which I will use for generating. Okay, now we know that nu tilde 0 is my clean images. Okay, and nu tilde 1 is Gaussian noise. All right, so these are the sort of 2 ends of this process. And how do we do this noising process? Well, basically what we do is we just like remove x0 and add noise according to a schedule determined by alpha and beta. There's many possible alpha and beta schedules. We're going to use a variance preserving schedule from this paper here. But yeah, the idea is that you're sort of adding more and more noise until eventually you reach junk. Okay. So low T, my XT tildes, my training T's are close to the original data. High T, this is close to Gaussian. Okay, so what this is doing is this is giving a sequence of distributions, which, you know, on one end are like absolute noise junk, and on the other end are my target. Okay, so maybe this sequence of distributions can then be used to train a sequence of MMDs. Okay, and that is what we do. Okay, so this is the loss that we're going to minimize to train our MMD features. Okay, now we're using as a kernel a particular expression here, which is a set of neural net features of X and neural net features of Y, the dot product of those features. So remember, kernel's dot product of features. So here they're trained neural net features. The features depend on time, right? So when the time is close to noise, time is close to 1, I'm going to have very coarse features. When time is close to 0, I'm going to have very fine features. And the thetas are the parameters of my neural net. But it's very important that these features are now time dependent. So different features at different times. And time equates to noise. Okay, I have a witness function here that also depends on time now, right? So when I'm close to noise, very coarse, very smooth witness function. Close to the target, very fine, very spiky witness function. Okay, and this witness function, of course, is parameterized by theta. All right, so this is the MMD. Now I've excluded, obviously, the red to red term because that doesn't matter. It's constant. Okay, I've only kept the blue to blue and blue to red terms. All right, Now I'm going to have a loss function at a time t that I'm going to minimize. And I'm going to use a couple of regularizations, which were taken from the GAN literature, because this MMD is also a GAN critic, and we can basically steal all of the tools that the GAN people thought up. Okay. One of these regularizers is a variance regularizer, so we want the variance of our features not to explode. The other is a gradient penalty regularizer, which is saying that the gradient of my witness function should not be too far from 1. So that shouldn't explode either. So these are penalizations which we took from the GAN literature and which we found were helpful to us. Okay, so we've added these penalty terms. This gives us a loss at a time t. The loss at a time t has the MMD, has a variance penalty, and has a gradient penalty. Okay, and we're going to minimize that with respect to the parameters theta of our features. And we're then going to actually not minimize this, but we're going to minimize the average of this over all times from clean to noisy. Okay, and so now we have basically a neural net that takes t as an input and gives coarse features if my t is close to noise, and fine features if my t is close to clean. Let's say that we've trained our sequence of MMDs. Now we have an algorithm to generate particles. How does that work? Okay, so first of all, I'm going to basically move in steps delta t, right? So these are sort of the, how large a step I take from clean to noise, which is a design parameter. So there's many, many design parameters in this algorithm. And then basically at every time step, so at every temperature, I take some number of steps using my witness function, evaluated at the optimum, for that temperature. Okay, so I just move my particles a little bit, some small number of steps at that temperature, then I drop my temperature, move my particles, drop my temperature, move my particles, drop my temperature, and eventually I get my target. So this is what we do. And the particles are moved using the witness function at that temperature. Okay. So how well do we do? So here is the table of us doing well. Here is the original MMD GAN. So basically this uses this adaptive GAN critic, but has a generator as well. And because it's got a generator, it loses some capacity. So this is FID, so smaller is better. We already improved considerably over the original implementation, which got a FID of 40. We got it down to 13. 13 is much better than 40. Okay, but these are the famous, I guess, Ho et al. DDPM diffusions. And these are way lower again, okay? So obviously, we're nowhere close to state-of-the-art on diffusion. What we managed to get with reasonable cost is this FID score here, which isn't too far off the same architecture used on a diffusion. So obviously, we have not put in necessarily the engineering effort to get it right to the state-of-the-art. But we're not too far off just from a fairly straightforward implementation. What we've compared against here are other gradient flows, other gradient flow approaches using either KL estimators or a sliced MMD estimator. But these ones are taught differently to ours. So remember how we taught ours. We taught ours by doing a forward diffusion process and then training our MMD on that. What these methods do is they just say, look, move my particles, then train my critic, then move my particles and train my critic. So they're actually training the critic on the particles that the critic itself generates. And this is a little bit unstable. It's adversarial, and the performance is, in fact, quite far off from state of the art. So I think, the solution basically of training on a forward diffusion process is what takes these methods and makes them work. Okay. So in all diffusion talks, we need to have a slide of pictures. Here's the slide of pictures. They're not so bad. We can also generate in high dimensions using diffusions in latent space. So this is something that we're playing with. But at this point, we're really getting into engineering and not into statistics. So I will leave that for this talk. So just to summarize, you can run Wasserstein gradient flow on MMD to generate particles that follow some target distribution. We did this using fixed kernels in this NeurIPS 2019 paper and using adaptive kernels in this iClear paper from this year. I should also emphasize you can also run this kind of gradient flow on a variational approximation to the KL divergence, which we call the KL divergence. That gives a gradient flow as well, which is a little bit better, I guess, at approaching target distributions that are defined on manifolds. There's also this deregularized MMD, which Hudson, who is here, and Anna have done, which basically uses a interpolation towards the chi-squared divergence in order to adapt the MMD as it's converging. So this is something which has, I think, really nice guarantees. Yes, and with that, I want to thank the sponsors of this work, Gatsby Charitable Foundation and Google DeepMind.
Thanks of all. First, thanks to the organizers for giving me the opportunity of giving this talk today with such a great lineup of speakers. And the work I'll be talking about today is joint work with Dennis and Andrew, where we explore we do a theoretical analysis of diffusion and in-Langevin Monte Carlo for generative models. So I'm going to disentangle this title along the talk. So I'll start with some motivation, and I'll mention the questions that we asked ourselves at the beginning of this project. I'll continue with some background on diffusion paths and in-Langevin dynamics, and then I'll get into the bulk of this work, which are the theoretical analysis or the obtention of non-asymptotic theoretical warranties for Gaussian diffusion paths and heavy tail diffusion paths. And I'll make sure later that the difference between these two is clear. So let's get into the topic now. So most of the works that, some of the works that we've heard today have been more in the sampling realm. I'm going to be focusing on the generative model or learning. So the aim of generative model is to learn the underlying probability distribution that we refer to as pi data given a set of samples. And nowadays there are a lot of generative models. One of the state-of-the-art ones are diffusion models. So this project started with us asking ourselves, what makes diffusion model perform so well? What makes them being so widely used these days? So to understand this, we first need to know how do diffusion models achieve generation. So first of all, they use a forward process, as Arthur has mentioned before, that goes from the data distribution, it adds noise progressively until we reach something that is close to a Gaussian distribution using a forward SD. And then, thanks to theorem from the 1980s from Anderson, we have a closed form for the reverse SDE, given the coefficients of the forward SDE, that allows us to go from our final distribution to the original data distribution that we are trying to learn. So there are a few things here that it's important to mention. So regarding the forward process, we have the choice of which forward process to use. And on the other hand, another key point of diffusion models is the reverse SDE, where we have this score function that is not available in closed form, so it's intractable and needs to be learned using neural networks. So these PT are the marginals of the forward process that are expressed through a convolution that I'll present later. So as I said before, we have the choice of which forward process to use. And in the diffusion model literature, one of the most commonly used forward process is the Ornstein-Uhlenbeck process. So the Ornstein-Uhlenbeck interpolates between the data distribution and a Gaussian. However, as Arthur has also mentioned before, this is done in infinite time. However, practitioners, they don't have infinite time, so they only run up to a time capital T. So this means that the final distribution of the forward process is not exactly a Gaussian, and we need to account for this error when analyzing the error of diffusion models. On the other hand, regarding the generation process or a reverse process, we have that the intermediate probability distributions, which correspond are the same as the forward process, can be expressed in this way. So if xt are random variables sampled from the intermediate probability distribution mu t, we can express them as the sum of two random variables for a specific choice of the schedule function lambda t. So for the OU process, this lambda t corresponds to this expression over here. So this means that for time 0, we have that this is equal to e to the minus 2 capital T, meaning that this lambda t would be very small. So the set component will dominate. In the case of diffusion model, this set component is a standard Gaussian distribution. Whereas for t equal to 1, we have that this term cancels out. So this one remains, where x is sampled from the original data distribution. So here, a few things that I would want to make clear are this mu t, since we can express xt as the sum of two random variables, mu t, the associated distribution, is given by a convolution. And another thing that I want to make clear so that we don't get confused later is that unlike diffusion models, we treat capital T as the final time corresponding to the data distribution. But in diffusion models, the data distribution corresponds to the initial time because they consider this like forward and backward process. So we thought it was more intuitive and also closer to the sampling literature, where your original or mu0 corresponds to your distribution that is easy to sample from, and mu capital T is your target distribution that you are trying to learn or trying to sample from. Another motivation that gave rise to this work is we have understood that the key point on diffusion models is this reverse process, so finding a path of probability distribution that can easily interpolate between the easy distribution and our data distribution. But there are also other classic paths that are used out there. So why are the diffusion paths better than other sampling paths, such as the geometric path that Anna presented here before? So as Anna said, and I'm also gonna use one of the samples that he used before to motivate the diffusion path, is imagine that we are trying to learn this data distribution that is given by a mixture of a normal distribution and a smoothed uniform component. So when m is equal to 10, we have here that the weight of the uniform component becomes very small. So pi data is unimodal. However, if we use an auxiliary or base Gaussian distribution, and we compare the performance on the geometric path given by this geometric mean between the data distribution and the base or Noising distribution nu, against the performance of the Gaussian diffusion path, where we have this Gaussian convolution that is the probability distribution associated with the sum of random variables that I presented before, we can see here that when starting from a Gaussian distribution and trying to get to the final distribution, we can see what Anna showed before this morning, where along the path there appears some multimodal behavior that makes harder to sample from this path. However, for the diffusion path, the path stays unimodal throughout the whole time, meaning that it has better properties because it's always easier to sample from something that is unimodal compared to something that becomes multimodal. So to formalize this mathematically, what does this, why is it better? So Rocco and Anna has talked about this log Sobolev constant. So this log Sobolev constant is a relaxed notion of strong convexity. So it also characterizes the convergence of Langevin diffusion, for example. So in the case of the diffusion path, we have that if the data distribution has a finite log Sobolev constant or respectively Poincare constant, and we're using a Gaussian diffusion path, meaning that the auxiliary distribution nu is Gaussian, we can show that the log Sobolev inequality and the Poincare constant stay bounded throughout the whole path by the worst constant of pi data or the constant of the base Gaussian distribution. And this is regardless of how far these two distributions are. So this is another motivation for using the diffusion paths against, for example, the geometric path. So one of the key things that I want to emphasize is that it all boils down to finding a path of probability distribution that can interpolate between the two distributions, so our simple base distribution and our complex data distribution. And this interpolation perspective has already been investigated in a recent work by Albergo and collaborators, where they explore what they call stochastic interpolants. And in particular, the one-sided stochastic interpolants that they call is in the case where they fix one of the two distributions to be a Gaussian distribution. So this would be exactly the same as the setting our like Gaussian diffusion paths. However, one key difference from their work to ours is that the way they sample from the path is different. So the way they sample from the path is same as in diffusion models. We have that the solution of the intermediate of the SDE have the same. So the solutions of the SDE, of the reverse SDE or the SDE used for sampling from the stochastic interpolants, has the same distribution and as the marginals from our path. So by using that SDE, if we are able to solve that at sampling in continuous time, we ensure that we are sampling from the correct path. However, to be able to get that SDE in the case of stochastic interpolants, we need intractable control term that needs to be learned using neural networks. So we take a slightly different approach, and we also consider these general linear interpolation paths. However, we are not restricted, as in the diffusion models case, to the Ornstein-Uhlenbeck schedule. We can fix lambda t to be any schedule under some assumption that I will introduce later. And instead of introducing control terms to sample from this path of probability distributions, we will explore the behavior of anneal Langevin dynamics to sample from this path. So this is the last time I mentioned this, but I think this is something that I would like you to take home with you, is that this reverse diffusion process is equivalent to sampling along a path of probability distribution given by this convolution over here for a specific schedule that we can choose. So if we in particular choose lambda t to be equal to 0 for t equal to 0 and lambda capital T to be equal to 1, we ensure that the initial distribution will correspond exactly to nu, unlike in diffusion model where we're starting from something slightly different from a Gaussian, and will achieve in a finite time pi data. So since, as I said, the reverse process cannot be described by a closed form, we need to introduce intractable control terms. We decided to use this time inhomogeneous Langevin dynamics which can be written in this way, where mu t corresponds to this distribution over here. However, we do a time rescaling using this kappa parameter to run this for slightly longer to make sure that the transition between the different distribution along the path is slower to ensure a better convergence. So this is a SD, but we need a specific discrete time algorithm to be able to do this in practice. So we decided to explore the behavior of using a simple Euler-Maruyama discretization. And another point is that this score term is not tractable, so also needs to be learned. But since we have access to samples from the original distribution, we can use the noising score matching techniques to learn this score function. So as I'm sure like everyone knows, Langevin dynamics converts exponents, converts asymptotically to the stationary distribution. However, if simulated in finite time, it has a bias, meaning that the solutions of this XD don't have exactly the distribution of the marginals of the path that we are trying to sample from. So this is bad news, but we're going to quantify this bias non-asymptotically. So this give us some good things that because we are able to carry out this work. And a key component that Anna mentioned before that will be the action. So what is exactly this action of the curve of probability densities interpolating between the base distribution and the data distribution? So this action serves as a measure of cost of interpolating between the base distribution and the data distribution. So in mathematical terms, this action can be described as the integral along in between like time 0 and time t of this derivative in Wasserstein distance. So this intuitively means that if the path changes very fast, this action will be larger because it's harder to adapt to those like fast changing to a fast changing path. So we want something that changes smoothly, a path of probability distribution that changes smoothly between our target and our base distribution. So this action, as I said, allows us to quantify this bias between the diffusion anneal Langevin dynamics. So the solutions of this SD and the exact path given by the convolution that I showed before. So using Girsanov theorem, we can show that the KL divergence between these two paths is given by the action times the time rescaling parameter kappa. So in particular, practitioners only care about what happened in final time. So using a data processing inequality, we can show that the KL divergence between the data distribution and the final time distribution from the diffusion and in Langevin Monte Carlo is bounded by the KL between the two paths, and this is bounded thanks to this theorem that we prove by the action. So provided that the action is finite, I'll provide later some conditions under which the action will be bounded. We can ensure that the KL between the data distribution and the distribution that we are, like the path that we are sampling from, is bounded. So using this, we can choose kappa in such a way that we ensure that that KL divergence is bounded by epsilon square. So any questions up to here before I get into the Gaussian diffusion paths and heavy tail diffusion paths? So it's because it's concerned with the metric derivative. And so the way the way traditionally the action is defined is with the basis time to distance, and it's also because you need to have like, I guess you can also define a similar notion of action in basis time p. But so I guess in this case we care about basis time too, because like this scale using Kirsanov theorem is given by the integral of the L2 distance between the components of the drifts of the SD. So in that case we care about the L2 norm, which corresponds. Yeah. So I guess like you can define a similar notion of for in basis time p. I don't know whether it would be. Yeah. For this one, so you need some assumptions on the path, some regularity assumptions, for example, having a finite moment. So you need assumptions for the action to be finite, mainly, and for Kirsanov theorem to hold. But these are fairly general assumptions on a path, some regularity assumptions on the path. I'll introduce some assumptions, some harder assumptions for the discrete time bound. Okay. So some initial assumptions that are fairly common in the diffusion model literature, like theoretical community, are this L2 accurate score estimator. So this says that the score estimator is epsilon square accurate. And then the other assumption that is also fairly general is that pi data, so the data distribution, has a finite second order moment. So one thing that I forgot to mention here is that we will be looking at non-asymptotic theoretical warranties for the cases when this new distribution is a Gaussian distribution, but also when nu is a heavy tail distribution. Because there have been recent work on heavy tail diffusion models. Because if for example, our data distribution is heavy tail, it will be better to noise using a heavy tail distribution rather than with a Gaussian distribution. So regarding the Gaussian diffusion path, so the case where nu is a Gaussian distribution, we have some building blocks for the analysis. So these two building blocks would be the smoothness of the path, which means that a grad log mu t needs to be Lipschitz constant along the path, and a bound on the action that is related to the previous theorem that I showed. So this smoothness assumption, or gradient log Lipschitzness, it's in general hard to verify. So it's unlike for the geometric path, where the score of the path is given by interpolation of the two scores. For the diffusion path, since the probability distribution is given by a convolution, there's not an easy way to compute the score. So it's not easy in general to verify this assumption. So in the paper, we provide alternative assumptions that are slightly stronger, under which it implies that the path is grad log Lipschitz is grad log Lipschitz. So one of the assumptions that we provide is that if we have strong convexity outside of the ball, so in particular, we require that pi data has a density with respect to the Lebesgue measure of this form, where the potential needs to be Lipschitz continuous, and also strongly convex outside of a ball that Anna mentioned before. So for example, like if we have like a mixture of two Gaussian, we have that outside of a ball for example, in 1D, we have a strong convexity. So in the mixture of Gaussian case with same covariance, it holds. It also holds for a mixture of Gaussians with different diagonal covariance. And for full covariance, we need some assumptions of the covariance for this to hold. So if you have any questions, feel free to ask, or like you can take in the paper. And under this assumption, we obtain a bound on the Lipschitz constant, LT, across the whole path that doesn't have a dimension dependent, but it has exponential dependence on the radius R and the Lipschitz constant L pi. So in the work that the second work that Anna presented today, they also obtain an alternative bound on the Lipschitz constant that has a dimension dependence, but doesn't have any exponential dependence. So regarding the assumption that we need to impose to get a finite action, this concerned having a finite second order moment. That is one of the initial assumptions that I introduced before. And we also need an assumption on the schedule. So we need the schedule to be non-decreasing, weakly differentiable, and also to satisfy either of these two conditions. So this condition is satisfied when the schedule is very flat towards like close to zero. So why is this intuitive? Because, for example, if we have a mixture of two Gaussians, so we have two well-separated modes, and we're starting from a Gaussian distribution in the middle, the mass will separate to target those two Gaussians. But for example, if they have different weights, it is gonna be key in the initial stages to have a correct separation of the mass. Because if the mass is incorrectly separated and not so the mass is incorrectly separated, we will get incorrect weights. And once the mass has separated, it's very hard to jump between the two modes. So therefore, the initial stages are key, meaning that having a slightly slowly increasing schedule can help for this mode separation or mass separation. Sorry. The second condition is satisfied when both we have a slowly increasing schedule at the beginning, but also a flat schedule at the end. And why is this intuitive? Because it helps to achieve a more detailed generation at the end. So, for example, a cosine-like schedule, like the blue, will satisfy this assumption, and also sigmoid-like or hyperbolic tangent schedules. So, under this assumption of the schedule, variable xt that is sampled from our intermediate probability distribution mu t is given by a sum of two random variables. We can exploit that to get this bound on the action that is bounded by the second order moment of the data distribution, the maximum of the second order moment, and the dimension up to some constant. So if we have for any epsilon, which is of the same order as the error for the score estimator, and we have smoothness assumptions on the path that is like grad log mu t is Lipschitz continuous. We also need finite second order moment and the assumption of the schedule that I introduced before. We have that the Gaussian diffusion and in Langevin Monte Carlo can be initialized with at the correct marginal requires this number of steps to approximate the data distribution in KL divergence with epsilon in epsilon square. So here we can see that we have this epsilon c is dependent, and if, for example, d is greater than the second order moment, we have a d square dependence here. So unlike the geometric path, where they, for example, like the other work that Anna mentioned this morning by Gao et al., they get a bound which is given by the axion, because they're not able to obtain a bound on the axion. However, thanks to the diffusion path, we are able to obtain this bound on the axion, and therefore give a complexity bound in terms of the parameters of the data distribution. So now regarding the heavy tail diffusion path, so the case where our noising or auxiliary distribution is a T distribution, we'll be also providing an analysis in this case. However, we need that the tail index alpha is greater than 2 to have a finite axion, because otherwise we are not able to obtain a meaningful bound on the axion. So some bad news for us, which make the analysis much harder, is that the T distribution is not a stable family. So this means that if we convolve two T distribution, we don't have a T distribution again. The building blocks for the analysis in this case are also the same as for the Gaussian diffusion paths. So we also need this smoothness assumption on the path, and we also need a bound on the axion, which is given by some assumption on the schedule. So again, as before, it's not easy to find the log the Lipschitz constant for this intermediate score, for these intermediate scores. And this is especially harder because we don't have a Gaussian distribution. We now have a T distribution. However, under this assumption, we can show that this assumption implies that the scores are gradient, are Lipschitz, sorry. So this assumption said that we need pi data to have a density with respect to the Lebesgue measure. We need grad log pi data to be Lipschitz with L pi constant. And we also need this bound on the score almost surely. So this can be a bit hard because it's not a bound on expectation, it's a bound almost surely. However, for example, for a T distribution like outside of some radius, this could be 1 over x, meaning that this is bounded almost surely outside of a compact set, and then inside of the compact, everything is nice. So in particular, this assumption is satisfied when our data distribution is given by a convolution of a distribution that is supported on a compact set and a T distribution. Again, the assumption that we require on the schedule is very similar to the one that we require for the Gaussian diffusion case. However, in the previous case, we have two alternative assumptions. In this case, we are restricted to one of them. So in this case, we need the schedule to be slowly increasing at the beginning and also flat at the end. And so under this assumption, a finite second order moment of the data distribution and the tail index of the T distribution that we are convolving with being greater than 2, we can recover this bound on the axion, where we have again here this second order moment, and here this is this has a dimension dependence here. And then we see that as alpha increases, this tends to 1, recovering the same bound that we got for the Gaussian diffusion path. So in this case, when we have that the tail index of the Noising distribution is greater than 2, and same assumptions that as the Gaussian diffusion case. So smoothness, finite second order moment, and assumption of the schedule. We have that this heavy tail diffusion and in Langevin Monte Carlo, when initialized from the correct distribution, has a complexity of this order to approximate the data distribution in epsilon square accurately in KL divergence. So again, we have here this square dependence Lmax that refers to the maximum Lipschitz constants across the path, and this epsilon 6 dependence. So one thing to highlight here is that this complexity bound is the same as the one that, it's the same as the one that we got for the Gaussian diffusion case. This has to be taken with carefully, because this is an upper bound, and this doesn't mean that this is the tightest one, but we just get the same upper bound for both Gaussian diffusion path and the heavy tail diffusion path. So just some take away messages. In this work, we look mainly as this reverse process or sampling from a path of probability distribution that interpolates between the simple distribution and the data distribution that we are trying to generate from. We obtain non-asymptotic theoretical warranties where we use an anneal Langevin dynamics to sample from that path of probability distributions when the data distribution is, the original distribution, or base distribution is a Gaussian, and also for a heavy tail distribution. And in the paper, we also obtain bounds for the Gaussian diffusion path under some weaker assumptions. So instead of requiring here, here's the same, here a assumption on the score of the intermediate distribution, we can derive complexity estimates when we just require this 8 moment to be bounded. So this might seem a bit strong, but when the data distribution is heavy tail light, this gradient of the potential would be something proportional to x. So this would mean that the 8th moment is bounded, which, for example, in a Gaussian case, this will satisfy. And for a heavy tail case, this is of order 1 over x, meaning that this will be also finite. And some future directions that we like to look at are more efficient numerical schemes so that we can obtain tighter bounds, or applying this framework that we've explored here to other generative models.
Thanks for staying and surviving so far. All right, so our last talk, the last session and the last talk will be given by Jonas. Jonas is a very nice guy. That's my introduction of him. He's really nice. He is at the University of Manchester by Department of Mathematics. He's an applied mathematician, as he likes to say. And he's going to talk about how to be the Bayesian adversary. Floor is yours.
Yes. First of all, thank you so much for the nice invitation and for the nice organization of this great event. Thank you also for putting me last. I learned this is the most important spot because shouldn't make people upset before dinner. Yeah, so I'll try not to make anyone upset. You kind of set me up for failure though by saying that I'm a nice guy, which, it's about okay. I mean, it's probably not exactly true, but fair enough. Exactly. So I'm an applied mathematician, and that means that I come up with paper titles like a machine learner. But I send papers to applied mathematics journals, so where they're underappreciated, not being read by machine learners then. Yeah, so it's setting myself up for failure as a scientist. I'm very sorry, I just need to hide this bar, otherwise I don't see my... Yes. Wait. It's visible to me, it's kind of, I think it disappears after a while, okay. Or I can always kind of guess what the paper or the title of the slide is. Okay, anyways, as I just said, so there's a paper connected to this talk. It's supposed to appear soon in the European Journal of Applied Mathematics. And the title of the paper is actually How to Beat a Bayesian Adversary. It's with my friends here. So as a little bit of a career advice to PhD students here. So actually Kei-Shin was in her first year of a PhD when she emailed me to write a paper together. She graduated like a few weeks ago, and we wrote 4 papers since then. So feel free to reach out to people when doing a PhD or doing a postdoc or at any point. And my other 2 friends, actually Xian is currently finishing his PhD, I think. Sheng is a postdoc in Delft. And I think those 2 are both on the job market. So in case you're looking for a postdoc, please hit them up. Okay. I will start with a very brief introduction to just giving like a setup to what I will be talking about, which is adversarial robustness in deep learning, and kind of with the speciality of having Bayesian attackers. And I will kind of tell you what a Bayesian attacker is, because that's kind of a concept we came up with, and then actually tell you how to prevent Bayesian attackers afterwards. And kind of this sort of how to prevent them will be like a fairly theoretical part of the talk. And then after that, we kind of talk about, okay, how do we actually do this in practice now, after we've mastered the theory? So there's a discretization section, and then we do some, okay, I call them numerical experiments. You may call them deep learning experiments. I guess there's not really much numerical analysis in there. It's just kind of testing the methods and then concluding afterwards. Okay. So I like to kind of explain supervised learning in the following way. We have some pair of random variables y and z with some distribution from the distribution mu. And our goal is to find a hypothesis g, that's just a function, such that this integral is minimized, and this integral is the so-called is a generalization error, where L is some kind of appropriate loss function. And if we have a g that actually does that, then we may use that function g to predict labels. Yeah, so the z's are called labels. From inputs, the y's are called inputs. Exactly. So when we have a y, we kind of would like to know what is the associated z. So we kind of just plug it into g and then get our answer. This whole process is complicated because usually we don't have free access to mu. We only have access to some samples of mu. Okay, so we've observed some k samples, yeah, y1, z1 up to yk, zk. And so the only thing we can really minimize is the empirical error. That's the best we have. And then we actually need to, we cannot really do it for like any function g, because that wouldn't really give us a small generalization error afterwards. So we need some parametric representation of g, which, okay, we need to represent g on our computer, but also to regularize the whole problem, yeah, so that we can actually learn from the empirical data to generalize well afterwards. Okay, and of course, I mean, you can think of linear regression if you want to, but I mean, I think this is kind of a slightly cooler problem, say like image classification in a Cypher-10 data set, where all these like y's are like small images, and the z's are labels of the small images. In that case, okay, linear regression probably is not really possible, but you may use a deep neural network instead. A neural network, I mean, you've probably seen this all before, just for the setup. So it's just kind of, we construct like some sequence combining linear and nonlinear functions. And these linear bits will be trained from data. So these are our parameters. And the nonlinear bits we determine beforehand. Okay, so far so good. Now, what are adversarial attacks? Try not to break anything here. So the problem is that deep neural networks usually approximate sort of discontinuous functions. Yeah, so classification would be something discontinuous, and that does make them, yeah, sort of attackable by an adversary. What does that mean? That sort of means that if I have a neural network that is trained on some data, I'm very often able to just perturb the data input a little bit and actually change the output of the neural network by just a small perturbation. Perturbation here is always is a directed perturbation. So it means I actually show you what it means in just a moment. Kind of just adding random noise usually doesn't work. Yeah, so that would not be, so that's usually fine. But the directed perturbation can mess things up. Yeah, so here's an example from the everyone's favorite MNIST data set. So it's an 8 on the left. There's a perturbation that you can't really see on the right. Yeah, on the right it really looks like an 8, still. But the prediction is now not 8, it's actually 3. Okay, and so I'm not sure what the size of the perturbation is here, but it's probably extremely small. And that's the whole idea. There's kind of one problem I'm quite excited about. So this is from a paper from of mine called Adversarial Inc., where kind of, okay, you could sort of say, okay, here you could maybe figure out that it's perturbed by just looking at like the black area around the 8 and say, okay, it's not actually flat, but it's quite noisy. But they actually managed to perturb MNIST and similar data sets by just perturbing like the colored area, like here on the right. Yeah, so there's no weird noise in the white area. They just perturb the black area, and that's enough to turn labels of these MNIST images. They have done even, I've seen in a talk from them even crazier stuff where they change like entire sentences in a text, handwritten sentences in a handwritten text, but it's not in the paper, unfortunately, so I couldn't steal it for this talk. Okay, now the question is, okay, so how does this work in practice? Okay, so we kind of assume that the attacker has actually access to the neural network, which of course is kind of like a big assumption to make, but that's usually what we assume. And then the attack is found by maximizing like the loss function by saying here, okay, we maximize over perturbations psi that are added to the input data. And we just, okay, we say, okay, the perturbations will be very small, so we just choose psi in an epsilon ball around the input. Ball is here, obviously L infinity ball. I guess other balls work as well. There are also other ways of adversarial attacks. You can also attack the weights of the network, or you can do all kind of stuff, but we just talk here about input perturbation. You can also, and kind of here we just say, okay, we just maximize the loss, which just means like try to mess up the prediction, or in binary would probably be then to flip the label. You can also have like actually directed adversarial attacks where you say, okay, but I want this 1 in MNIST to look like a 0. Yeah, that's possible as well. Yeah, so there's a whole slew of different methods. Okay, what do you do to counteract that? So instead of just minimizing, as we said in the beginning, just minimizing the loss, the empirical loss, we now try to minimize over these adversarial attacks, okay, which gives us this min-max problem here. Yeah, so we minimize over the mean of all of the adversarial attacks on all of the data. Which, okay, kind of looks like a saddle point problem, and saddle point problems are something we understand well, but then, okay, but then this is all non-convex and awful, and so there's not really a saddle point problem we understand at all. This inner maximization we can't really do either, yeah, because it's actually quite costly itself. And so what is usually done in practice is kind of a very coarse approximation to the inner problem, and then minimizing over those coarse approximations of the inner problem. Yeah, and that actually works quite well. So there's this method, the fast gradient sign method, where we just say essentially we do one gradient step within the epsilon ball. Yeah, we just figure out, okay, which direction we need to go, multiplied by epsilon, and then we kind of end up on the ball. And that's then enough for the inner problem. There's kind of some alteration to it, and I mean, there's like a whole zoo of other methods. I mean, this was really popular like a few years ago. I'm always like a few years behind popular topics. Welcome to my life. But yeah, I guess it's popular now again. Okay, it's late. I'm allowed to. Okay, and one problem is, okay, I mean, you could say, okay, this works quite well in practice, but then we don't really know why, and so that's like a bit sketchy. So maybe there's something we can do that we understand better, and that was kind of one goal of this work. Okay, let's talk about Bayesian adversarial attackers. So if we did Bayesian learning or kind of Bayesian machine learning, we would kind of instead of minimizing loss function, we'll probably use something like a generalized Bayesian approach. Like there's not really likelihood here, but we could just say we take e to the minus the loss function as a likelihood. Yeah, it's called generalized Bayes usually. And we have some prior on the weights. And then similarly, we could actually say, okay, I mean, maybe we don't do this as a learner, but maybe we do this as an attacker to kind of try to counteract what the Bayesian learner does here. And that would just mean that instead of maximizing the loss function, we would just take like e to the, some parameter times the loss function as our likelihood. And we say, okay, we don't really have preferences on our ball, so we just take the uniform uniform distribution over our ball as a prior. Okay, so this would just mean that just answering the question, how would somebody that's like Bayesian statistics more than optimization, how would they try to attack a neural network? These distributions are like a little bit weird because I mean they look a bit like likelihood as we know it, but there's no minus in front of the potential. So they don't really focus on a point or anything. They should actually do kind of the other way around, the other thing. So they should actually give like a small mass to the originally learned prediction. It should give a large mass to kind of everything that does not agree with the original prediction. And can I kind of look a bit like this in a simple example? We kind of say, okay, we have two parameters now with epsilon, that is the size of the ball, and we have gamma, that's like an inverse temperature. So gamma determines sort of how focused we are around the maximizer, and epsilon like how big the perturbation can be. Okay, so if epsilon is quite large, then we have a wide area the distribution is concentrated on. If gamma is large, then we essentially all the mass is on a single point. Although it's still on the whole, but most of the mass is around a very small point. Whilst if gamma is rather small, then we are almost uniform on the whole ball. Okay, so that's the idea. Now, we can interpret this in a Bayesian way. We can also just say, it's kind of it's like sort of a kind of a simple relaxation of the original problem. So actually with this gamma and kind of if it's in tempering today, if you think of simulated annealing or something like this, then you would kind of see, if gamma goes to infinity, then we converge to the maximizer or to a Dirac in the maximizer in the point, or actually to a uniform measure over all maximizers of that point, like under some regularity assumptions, of course. And it would sort of mean that actually the Bayesian adversarial distribution converges to the uniform distribution over all of the maximizers of the adversarial attack. And then we're actually back to the original problem. Okay, so we could just see this also as a simplified version. So this adversarial robustness problem as a simplified version of the original min-max problem. Okay, because that's the idea now. Rather than having a min-max problem, we have a minimize over integrals problem, which looks a bit more comfortable than a min-max problem. There are already other ideas. So actually this second paper here, they kind of suggested this as well, just in a fully discrete setting. So all the attacks were on a discrete set, and they did this kind of in parallel to us. And we were just happy that somebody else did this as well. It's actually quite nice if you're not the only one thinking something is a good idea. But they did more in the PDE setting, I think. Okay, the question is now, how do we solve this minimization problem, this new Bayesian adversarial robustness minimization problem? So first of all, I kind of simplify my life a little bit for like the next like 10-15 minutes or so by saying that we have only a single data set. Which I mean later we kind of discuss what happens when you have large data sets, and we kind of give some strategies. In that case, it just minimizes writing stuff or simplifies writing stuff quite considerably. So we have only one data set, and we kind of like redefine the potential phi to just depend on xi, which is the attack, and theta, which is the parameter. So we don't have to worry about y's and z's for some time now. And now, obviously, it's a gradient flow meeting, so we would like to minimize this using a gradient flow. Now, what is nice is if I kind of write down the gradient of this function f here, that I just call f now the target function, it actually has a fairly fairly pretty form. Yeah, so we just get a gradient here over phi integrated plus some covariance term between phi and the gradient of phi. Okay, that's a surprisingly simple term. Where of course covariance is just this down here. Let's not talk about that too much. The thing is, obviously, I mean, this is kind of a nice formula. Obviously, we can't evaluate this analytically, yeah, because there's kind of a complicated distribution that we need to integrate with respect to. Also, we can't really use stochastic gradient descent, because in stochastic gradient descent, we would need to sample independently from those distributions, which we can't. Yeah, I mean, usually, okay, these can be very high dimensional if you have high dimensional data. Yeah, so that's not really a good strategy to do that. What we could, of course, do is, and what we will do is use some MCMC ideas, so use some overdamped Langevin dynamics to sample these. Also, like, we don't do accept rejector here. Yeah, I mean, it doesn't have to be that precise, probably. And okay, we choose them in this way with reflecting boundary conditions, yeah, so that we get these Bayesian adversarial distributions as stationary measures. And okay, and then we can actually show that we converge to those as t goes to infinity, but then we can't really wait that long. Yeah, so I cannot really say, okay, we do stochastic gradient descent. We kind of always simulate Markov chain and then plug that thing in, do one gradient step, simulate another Markov chain. We don't really have time for that. So that would be too complicated. What we do instead is we use the same idea as some people in this room have used before. And that is, we actually simulate Langevin dynamics in parallel to the gradient flow. We use multiple of those, and then we sort of, I'll show you the formula on the next page, but we kind of couple the gradient flow and the Langevin dynamics at the same time, and then get a particle system that approximates the complete gradient flow at once. This looks a bit like this. We call it the adversarial Bayesian particle sampler, or for short APRAM. That was not my idea. It was the idea from an online tool that comes up with acronyms. So you can't, if people say, oh, that was a silly acronym, it's not my idea. Yeah, so you can't blame me. But it looks a bit like that. So we have this gradient flow approximation here. Yeah, so what was a mean before is now a sample mean. What was a covariance before is now a sample covariance. And we get these samples from these n seemingly independently running overdamped Langevin dynamics. Seemingly independent because obviously they're all coupled via theta, yeah, via the gradient flow, and then they're not really independent, but they look a bit independent. Obviously, okay, and we kind of formalize this in just a moment, but obviously these are chosen again such that they are reflected on the epsilon ball. Yeah, so we still stay within the epsilon ball. Yeah, that's important. Okay, yeah, some visualizations. So I kind of just simulated this for like a very simple problem. Yeah, so it's just kind of looks a bit like linear regression or so. Where we have here a setting with so it's only 3 particles, and I think we have so on the left hand side the value for gamma is a bit larger than on the right hand side. We kind of see here we're very much hugging the boundary on the left hand side, whilst on the right hand side we sample much more uniformly. Okay, it's quite hard to see this. I kind of plotted the densities down here, but it's kind of difficult to see that this is more uniform than that one. Yeah, it's a bit difficult to see here. If I choose more particles, so now we have gamma equals to 10 on both sides. If we choose more particles, then kind of what we see is, okay, this path here, this kind of gradient flow approximation gets like a lot more stable over there, but then also more particles are obviously much more expensive than fewer particles. Okay, but just as visualization, yeah, we have a gradient flow and we have these particles that like approximate the integrals between the gradient flow at the same time. Okay, and now there's some questions and I kind of will try to answer. I mean, I kind of give some spoilers here already, but kind of one question is, do we actually find the minimizer of f, say under unrealistic assumptions? And the idea will be that we show that these dynamics converge to some so-called Makin-Vlasov SDE. And we show that under even more unrealistic assumptions that this Makin-Vlasov SDE can then find a minimizer of F. How can we employ these in practice? Yeah, because I kind of was talking about like SDEs and gradient flows now, kind of what do we need to do in practice to apply these? And does it even work? And it will be in the end. Okay, so first we talk about this so-called mean field limit. So we're wondering, okay, what happens to the system as n goes to infinity? So we kind of sort of rewrite R' once more. Maybe actually this is not super necessary, but just if it's done once formally, this is the same process as before. We just kind of write it in terms of these empirical distributions here, just to have introduced those as well. And then we have this extra term to the right that is the actual formal version of keeping something on the epsilon ball. Yeah, rather than just saying that it is there. That's kind of how it's formalized. Yeah. And the goal is to show that this converges to this the so-called Makin-Vlasov SDE. That is kind of a combination of something that looks a bit like an ODE here and something that looks a bit like an SDE, but then it's kind of a strange SDE because this ODE part here does not only depend or doesn't actually depend on Xi, but it depends on the distribution of Xi. Okay, so in order to simulate this, we would not only need to know what theta is at a given time, but we also need to know what the distribution of Xi is. So kind of one Xi is not actually sufficient. Yeah, we need kind of a lot of them at the same time, which is essentially what R' does already. Yeah, so kind of that's sort of kind of going backwards from saying, okay, we're a particle system, and then saying, oh, but there could be something limiting afterwards. But it's essentially just it's a particle system just with only one particle, and saying that, or assume that we are able to actually track the behavior of that particle precisely. Okay, we show convergence in the Wasserstein distance, that I will not explain, and kind of for notational convenience, we have this function g, which is a bit like the gradients that we try to approximate. Just here the distribution of which we approximate kind of is an input as well. Then we have some like fairly realistic assumptions, which is just we kind of just assume that things are Lipschitz continuous, and Lipschitz continuous in both. Yeah, so in the distribution and the particle and the perturbation, or in the parameter and the distribution. Okay. And then we can show this propagation of chaos result, which essentially just says that our R' gradient flow and our R' particles converge to the Makin-Vlasov SDE. Okay, as n goes to infinity, and that is at sort of different rates depending on what the dimension of the space is. Now this is kind of fairly, I mean, kind of these dimensional space you kind of also find when you, so like when you're wondering, so how Monte Carlo converges in Wasserstein, that's kind of the same type of result. So if you've seen it before, then this is not very surprising. Then secondly, the long-term behavior of the Makin-Vlasov SDE. So here, let me just see whether I still have time. I still have time. Yep. Actually, way too fast. Oh, you have to ask lots of questions later. Okay, and then secondly, okay, is the Makin-Vlasov SDE able to find a minimizer? And this is where the pure hypocrisy begins. Yeah, so now we actually want this function g to be strongly monotone, which kind of means that phi needs to be convex as a function of the parameter. And of course, in a set of neural networks, that's completely absurd. But then, I mean, it's a gradient-based method, so there's usually not much else you can do. But all right. If we have both these assumptions, then what we can first show is actually f. So this function we want to minimize has at least one minimizer, which is nice. And then secondly, we can actually show that the Makin-Vlasov SDE also finds this minimizer. Yeah, meaning that the gradient flow part of the Makin-Vlasov SDE converges to the minimizer, and the distribution of the particles converges to the Bayesian adversarial. Yeah, that might still work. Yeah. Okay. And yeah, exactly. And so the particle part of the McKean class of SDE converges to the Bayesian adversarial distribution concentrated in the minimizer. And this happens at exponential speed, actually. So this is actually quite fast. Okay, can I say anything about any of these parameters? Not really. Or any about these constants? Not really, unfortunately. Okay, so now we are persuaded that RPROM is the best method that's ever been created. Okay, have we? Yes? No complaints? Very good. Okay, so let's briefly talk about. Sorry, I don't do all the technical stuff. Please ask me afterwards or send emails to my much smarter collaborators. That's even better. But let's briefly talk about discretization because that's actually kind of important. How to apply this in practice. So that's kind of three things we need to do. Okay, we need to discretize some SDEs. We need to discretize some ODE. And we have to handle large amounts of data. And actually, kind of the first two are like sort of fairly trivial. The last one is a bit more complicated. So to discretize the SDE, the only thing what you just use is a projected Euler Maruyama. Yeah, so projected meaning whenever we leave the epsilon ball, we just kind of project back into the epsilon ball. As easy as that. And what we also do is, okay, we sort of say, okay, we let them run at the same time, the gradient flow and the Euler Maruyama discretization. But what we've seen actually is it makes sense to have like some more Euler Maruyama steps in between gradient flow steps, yeah, to just get a bit more mixing in the epsilon balls. So we actually usually kind of allow like a few more iterations if we feel it's necessary. So it's just an additional parameter, which in a way is just like a way of choosing different velocities for the particle system and the gradient flow. Okay, and what we also do is we actually initialize it with uniform noise, which is similar to what people have done before, which I think makes sense here because, I mean, if you have n particles, you don't necessarily want to start them at the same spot. You kind of want to distribute them already in the ball, and then they might mix a bit faster. For the gradient flow part, we do exactly the same thing. Yeah, so we use forward Euler. And then turn the gradient flow into a gradient descent algorithm. We still kind of assume that we still have only one data point. Okay, so the sum here is over the perturbation particles. It's not over the data. If we have more than one data set, okay, we can just do subsampling. You just say, okay, we pick one at a time. And essentially turn this into a mix of gradient descent or McKean-Vlasov approximation and stochastic gradient descent. The problem though is kind of choosing one at a time is like a little bit brutal. Yeah, because okay, you could have like a million data sets or so. If you choose one at a time, you will get a lot of noise in your gradients from data subsampling. So what people do in practice a lot in stochastic gradient descent is actually not choosing one at a time, but actually choosing a few at a time. Yeah, so this like so-called mini batching where we say, okay, for every gradient evaluation, we don't choose one data set, we choose like 50 or so, or 500. So because, I mean, obviously we don't want to take too many because then the gradient evaluations are getting too expensive, but we also don't want to have too few because then the gradient evaluations will be extremely noisy and they may not mean very much. The problem is if we do that here, we suddenly get a lot of things to do. Yeah, because for every data set, we would need to run n particles in RPROM because, I mean, we have different attacks for each data set, which is like completely impossible. Okay, so I can't really, I mean, if I like, even if I have just like five RPROM particles per data set of 500 data sets, I would have like 2,500 particles. I mean, that's not doable for an interesting problem. What we do instead is like a little bit,
Sorry,
yeah.
It doesn't sound that many. So why is it not doable? I'm missing it.
No, I mean, okay, like 2,500 sounds a lot to me actually, because we need to evaluate gradients the entire time through the networks, 2,500 times for each, and this would only be, so I take 500 data sets and 5 particles. So that's still kind of like a very weak, like on the RPROM side, like a fairly coarse approximation. So it just scales very quickly, it gets very large, number of particles get very large very quickly. So I wouldn't really want to do that. What we do instead is is a little bit sketchy, but it has worked for a different method. And that is, we actually say we choose as many RPROM particles as we have data sets in a batch. Then we actually say we give each of the RPROM particles its own data set. So we sort of say we actually kind of mix the two dynamics with each other. Actually, I have a plot for this. So instead of saying that all RPROM particles get the same data set at the same time, as would be usual in the SDE case, we actually say that each RPROM particle gets its own data set. Okay, and therefore we kind of mix two different ideas at the same time, but it does work really well. And there's no justification in the theory for being allowed to do that at all. Yeah, so that would be a good next step though. But there's no justification for that. Yeah, so we just say kind of each of the particles approximates only one data set or the attack to one data set, and then we mix everything at the same time, which we're really not allowed to do. We are allowed to do this in the Ensemble-Kalman filter. Yeah, so that's kind of where I stole this idea from. Okay, it's not really stealing when it's our idea, and that's also where I stole this figure from. It's not really stealing when it's our idea, but that's kind of why it's not really equispaced here, because it was a different method. But for the Ensemble-Kalman filter, you are allowed to do that. So you can do subsampling in Ensemble-Kalman inversion by giving different data sets to each particle. Here, there's no justification, but it works quite well. Okay, and it works quite well. Okay, I will kind of quantify this in terms of numerical experiments in just a moment. We also need to be able to actually attack in a Bayesian way, which we here just do exactly with the mechanism that we actually use to defend. Yeah, so we just sample the projected Euler Maruyama from our overdamped SDE. We kind of do two different kinds of attacks. Yeah, so either we like just generate this SDE chain and then attack with the last point, or we collect all these attacks that we sample here and we attack with the mean in the end. Okay, so these two different ideas. I mean, it kind of feels like very often it should just be the same. There could be an argument for the mean actually being worse, because like the mean of two different good attacks could actually be kind of a bad attack actually. But we just wanted to try both. Okay, let's see what happens. So we did two experiments. The first one was actually just MNIST, and we compared to this fast gradient sine method. And there we see, okay, that first of all, normal RPROM without mini batching is just doing quite poorly. There's not really a reason to do that. I mean, obviously, you wouldn't really do anything without mini batching, I think. Yeah, so the training is just quite bad in this case, and so you probably shouldn't do that. If we use mini batching, the results are fairly comparable to FGSM. FGSM is like usually like a little bit better. Yeah, that's sort of a shame. But obviously, okay, this is much more expensive than that. Yeah, so in that case, you would probably use FGSM. But then maybe MNIST is not the best problem to test something like this on anyway. So we then move to Cypher 10. And there we like things get a bit more interesting. I mean, there we see that kind of for most usual ways to actually attack the Bayesian or the RPROM method does quite poorly. What it is good at is, or better than FGSM, are Bayesian attacks. Yeah, so here we actually see that it does what it's supposed to do, that is preventing Bayesian attacks, so that's good. What is also surprisingly good at is actually preventing or like working in the non-attack setting, because it's kind of a usual problem in adversarial robust learning, is that you're really good at preventing attacks, but they're kind of awful at not being attacked. Yeah, which is obviously not really that good. Yeah, but here we get a significantly better accuracy at not being attacked than FGSM, and a significantly better accuracy when it attacks Bayesian. But in the other cases, we're not doing particularly well. But okay, we also haven't defended against them. I guess that makes sense. But so in that case, it's not so persuasive. We haven't even done like the non-mini batching version here because it didn't feel it was worth it. But the mini batching version worked quite well. Okay. Way too early. Okay, I will take very long with the conclusion. No, the Bayesian adversarial. No. Okay, so first of all, we have this Bayesian adversarial robustness problem. It can be interpreted in two different ways. So we can either see it just as a relaxation, sort of in a simulated annealing type perspective to the usual min-max problem. Or we could see it as a way to actually counteract contact a Bayesian, like some adversary using Bayesian, so approach to the attack. Yeah, so that's to solve this problem. We introduce the RPROM methods. RPROM, we can show that RPROM under fairly broad assumptions approximates some McKean-Vlasov SDE. Under quite specific assumptions, this McKean-Vlasov SDE can find a minimizer of the Bayesian adversarial robust learning problem. And so for a certain class of problems, at least we can give a justification for using this method. Then, okay, we talked about discretization of this. So we kind of use Euler or forward Euler-Maruyama, including some mini-batching version that is a bit sketchy, but quite efficient. And actually it's quite good at defending against Bayesian attacks. It's not so good at more traditional attacks. Yeah, but that's probably to be expected. There are lots of open questions. I just didn't have much space for all of them. But obviously, kind of one thing that would be interesting is actually in this particular case. So we kind of assume that we are traditional deterministic learners, because we just minimize a loss. But we think that the attacker is Bayesian. Kind of the setting where both are Bayesian would be interesting to figure out, obviously. And then kind of I think for many of you here, this is could be like an interesting like an interesting sort of example to test your methods on, because I know that these hybrid optimization problems are quite popular, and there are better ways to do that than with this like particular sample approximation. Yeah, that's like is a bit coarse. So maybe if one of you has a better idea on how to actually solve this problem, I would be all ears. And there's someone here waiting for the last picture. That will just persuade you to come to Manchester and visit me there immediately. Isn't it beautiful? Thank you all.